So here we are. The room is quiet, the day is done, and there is nowhere else you need to be right now. The only thing ahead of us is a long, slow walk through a question, one of the oldest questions people have ever asked while looking up at a dark sky. And that question, put simply, is this: are we alone? Is there life somewhere out there, beyond this planet, beyond this solar system, beyond the familiar stars we can see with our own eyes? We are going to spend some time with that question tonight, not racing toward an answer, not building toward some big dramatic reveal, but just unfolding it slowly, piece by piece, the way you might unfold a well-worn map before a long journey. There is no rush here. There is no test at the end. You do not need to remember every detail, and you do not need to keep track of names or numbers. If your attention drifts, that is perfectly fine. The words will keep going, soft and steady, and you can pick up the thread again whenever you are ready, or simply let the sound of them wash over you without holding on too tightly. This is a story about looking, and listening, and wondering, and it is told in the same slow spirit. The search for life beyond Earth is not a sprint. It is not a mystery that gets solved in a single night. It is something much gentler, a long, careful, patient unfolding of what we actually know, and what we still do not know, and what we are only beginning to learn how to ask. If you have ever stood outside on a clear night, far from city lights, and just looked up, you already understand the beginning of this story. For as long as there have been people doing exactly that, tilting their heads back, letting their eyes adjust to the dark, and feeling the quiet pull of all those points of light. Every single culture in human history has looked at the night sky and wondered what, or who, might be out there. The ancient Greeks spoke of other worlds. Philosophers in India and the Islamic world wrote about the possibility of life on distant celestial bodies. Long before telescopes, long before anyone knew what a planet really was, or how far away the stars were, the question was already there, waiting. It is a question that seems to come with being human, as naturally as breathing. And tonight, we are going to walk through that question step by step, not by inventing stories or imagining far-fetched possibilities, but by looking at what the actual search has looked like, and what it looks like right now. We will talk about what we mean when we say the word life, and why that matters when you are searching for it somewhere else. We will visit the places in our own solar system where scientists are looking most closely: the rusty surface of Mars, the icy moons orbiting Jupiter and Saturn. We will travel outward, to planets circling distant stars, and learn how anyone can even begin to study a world so far away that its light takes hundreds or thousands of years to reach us. We will talk about listening too, the long, quiet effort to catch a signal, a whisper, a sign that someone else out there might be trying to say hello. But before any of that, there is something important to settle into, something that makes this whole journey feel less urgent and more restful. And that is the simple fact that the search is still open. It has not ended in a great announcement. It has not ended in a quiet disappointment either. It is ongoing, right now, tonight. Telescopes in space and on the ground are gathering light as you listen to these words. Data is being collected, slowly, patiently, and scientists are studying it just as slowly and just as patiently. This is not a story that has reached its final chapter. It is a story whose pages are still being written, one careful observation at a time. And because it is still open, the phrase you will hear often tonight, in many different forms, is this: we do not know yet. That is not a failure. That is not a problem to be solved by morning. It is simply the honest shape of the question. We do not know yet if there is life somewhere else. We do not know yet if the conditions we see on some distant world really do add up to a living thing, or just a set of interesting chemicals. We do not know yet if a signal we picked up once was a natural event, an instrument glitch, or something else entirely. We do not know yet if intelligence is common in the universe, or vanishingly rare, or something in between. And all of that not knowing is not a source of anxiety tonight. It is a source of spaciousness. It means there is room to breathe. It means there is no final word to brace for, no verdict being delivered, no crescendo building in the dark. Think of it this way. Imagine standing on a shoreline at night, looking out over an ocean you cannot see the other side of. You know there are things moving in that water. You know there are depths you cannot reach. You can listen to the waves, feel the breeze, and let your mind wander across all that unseen distance without needing to map it precisely. That is the feeling we are aiming for here. The search for life beyond Earth is like that, a vast, dark, quiet ocean of possibility, and we are standing at the edge of it, listening. Some people spend their whole careers listening. Some spend a lifetime building better instruments to listen with. And still the ocean keeps its secrets, for now. That is not frightening. It is simply true, and true things can be restful. You might already know some of the names and places we will visit together. Mars, with its red dust and its dried-up riverbeds. Europa, a moon of Jupiter, with its cracked icy shell and the deep, dark ocean thought to lie beneath it. Enceladus, a tiny moon of Saturn, spraying plumes of water vapor out into space like a slow, cold geyser. Planets around other stars with names like Kepler 442b or TRAPPIST-1e, designations that sound more like catalog numbers than places, but which represent real worlds, real chunks of rock and ice and gas circling real suns unimaginably far away. We will meet all of them in time, and we will do so gently, without any pressure to remember their details. They are here to be contemplated, not memorized. The journey we are about to take is not a lecture. It is more like a slow evening walk through a familiar landscape, one where the guide points things out in a low voice and lets you linger on whatever catches your attention. If you find your thoughts wandering back to the image of that dark ocean or to a memory of a night sky you once saw, that is not a distraction. That is part of the walk. The facts and the names and the numbers are just the path beneath our feet. The real terrain is the wondering itself. And wondering, real wondering, does not require answers. It does not require certainty. It only requires a little bit of quiet and a little bit of patience and a willingness to sit with an open question without trying to close it too quickly. Tonight, we have all three. The quiet is already here, around you and within you. The patience is something we can practice together, one slow sentence at a time. And the open question, are we alone? Is there life out there? What else moves in the dark? Is the same open question that has been keeping quiet company with stargazers for thousands of years. So let yourself settle in. Let the day's concerns soften and recede. There is nothing you need to solve right now, nothing you need to figure out, nothing you need to hold on to. The story we are about to walk through is one of the most profound and careful searches human beings have ever undertaken, and it is happening whether you are paying close attention or not. It is happening while you sleep. Telescopes are turning on their mounts. Light from distant suns is falling onto mirrors and detectors. Data is streaming into computers, bit by bit, photon by photon. And somewhere, in all of that gathered light, there may be a clue, a faint, subtle signature that will one day reshape everything we think we know about our place in the universe. Or there may not be. Both possibilities are real. Both are part of the same patient search. And that search, at its heart, is not just about instruments and data and scientific papers. It is about a very old and very human impulse, the impulse to look out into the darkness and ask if anything is looking back. It is the same impulse that made shepherds and sailors and desert travelers look up, thousands of years ago, and name the patterns they saw in the stars. It is the same impulse that makes a child ask, for the first time, whether there are people on other planets. It is curiosity, plain and simple, the kind that does not demand immediate satisfaction, the kind that can sit quietly and wait. So tonight, we are going to sit quietly and wait together. We are going to walk through the landscape of what is known, and what is not known, and what is being explored right now. We are going to do it slowly, without hurry, without fanfare. You do not need to stay awake for all of it. In fact, if these words carry you into sleep somewhere along the way, That is exactly as it should be. The search will still be there in the morning. The question will still be open. And you will have spent some time in its company, which is all anyone can really ask of a quiet night. The sky outside, whether you can see it from where you are lying or not, is full of stars, hundreds of billions of them in our galaxy alone, and each one a sun, and around many of those suns, planets. The numbers are so large that they become almost impossible to feel. But you do not need to feel the numbers. You only need to know that the possibility is real, and that it is being explored, and that the exploration itself is a kind of tribute to the question. We look because we can. We listen because we are curious, and we do not know yet because the universe is very large and we have only just begun. Take a slow breath and let all of that settle. The question is open, the search is patient, the night is long, and we have nowhere else to be. But before we can go looking for life somewhere else, there is a quieter question we need to sit with first. It is a question that sounds almost too simple, the kind of thing you might think we already have a clear answer for. What do we actually mean when we say the word life? If we are going to search for it out there, among the stars and on distant worlds, we need to be honest about what we are searching for, and that turns out to be harder to pin down than you might expect. Think about it for a moment. If you look out your window at a tree, you know it is alive. If you see a bird land on a branch, you know it is alive. The grass, the insects in the soil, the bacteria on your own skin, all alive. But what is the thread that ties them all together? What makes something alive rather than not alive? A rock is not alive. A cloud is not alive. A flame can move and grow and use fuel, but we do not call a flame alive. So where is the line, and how do we draw it clearly enough to use it as a guide when we point our telescopes at a planet 40 light-years away? Scientists who study this question, the question of what life is and how it might arise, tend to work with a practical definition. It is not a perfect definition, and they know it is not perfect, but it is useful. It says that life, at least life as we know it here on Earth, needs three basic things. It needs liquid water, it needs a source of energy, and it needs a chemistry built around the element carbon. Those three things, water, energy, and carbon, are the foundation of every living thing we have ever found. From the simplest single-celled organism in a puddle to the most complex creature in the deep ocean. If you take away any one of those three, life as we know it stops. Let us take those one at a time, gently, because each one has its own quiet logic. First, liquid water. Water is, in many ways, the closest thing life has to a universal solvent. It dissolves other substances easily, which means it can carry nutrients into cells and carry waste out. It stays liquid across a useful range of temperatures. It expands when it freezes, which means ice floats, and that floating ice can insulate the liquid water beneath it, a small detail that may have been crucial for life on early Earth. Every single living cell we know of, every microbe, every fungus, every plant and animal, depends on liquid water to carry out the chemical reactions that keep it alive. Dry out a cell completely, and those reactions stop. Add water back, and in some cases, they can start again. Water is not alive, but it is the medium in which life on Earth does its work. The second requirement is a source of energy. Life does not run on nothing. It needs fuel of some kind to build itself, to move, to reproduce. On Earth, most of that energy comes, one way or another, from the sun. Plants capture sunlight directly through photosynthesis and turn it into chemical energy. Animals eat plants, or eat other animals that ate plants, and in doing so they tap into that same flow of energy, passed along from one living thing to another. But sunlight is not the only source. There are organisms that live in total darkness, around deep-sea hydrothermal vents on the ocean floor, and they draw their energy not from the sun, but from the heat and chemicals billowing out of the Earth's interior. These are the extremophiles, organisms that thrive in conditions that would kill most other life. We will come back to them in a moment. For now, the point is simple. Somewhere, somehow, life needs an energy source to keep going. The third requirement is carbon-based chemistry. Carbon is the backbone of every organic molecule we know of in living systems. It is the element that can bond with up to 4 other atoms at once, forming long chains, rings, and complex three-dimensional structures. That flexibility allows carbon to build the vast array of molecules life requires: proteins, fats, carbohydrates, and the nucleic acids that carry genetic information. Other elements can form bonds, but none of them do it with quite the same versatility as carbon, at least not at the temperatures and pressures where liquid water exists. Silicon, for example, is sometimes suggested as a possible alternative basis for alien life, and it is true that silicon can also form 4 bonds. But silicon bonds are generally less stable in water, and silicon-based chemistry does not produce the same easy complexity that carbon does. So for now, when scientists search for life, they search for carbon-based life, because that is the only kind we have a working understanding of. These 3 things, liquid water, an energy source, and carbon chemistry, are sometimes called the requirements for life as we know it. And that phrase, life as we know it, is one of the most honest phrases in all of science. It admits something important. It admits that we are working from a sample size of 1. We have only ever studied life on 1 planet. We do not know if life somewhere else would necessarily follow the same rules. It might use a different solvent instead of water, like liquid methane or liquid ammonia. It might be based on a different element instead of carbon. It might draw its energy from sources we have not even thought of. We simply do not know, and we have no way of knowing until we find it. But you cannot search for something without some idea of what you are looking for, and the most reasonable place to start is with the only example we have. So we search for water. We search for places where the temperature is right for liquid water to exist. We search for carbon-based molecules that might indicate the presence of living processes. This is not a failure of imagination. It is a practical choice, born of the simple fact that we have to start somewhere. Now, about those extremophiles. The word itself sounds technical, but it just means lovers of extremes. These are organisms on Earth that live in places we once thought were completely hostile to life. Places like the boiling, acidic pools in Yellowstone National Park. Places like the crushing, pitch-black trenches at the bottom of the ocean. Places like the dry, frozen valleys of Antarctica, where the air is so cold and so parched that it seems nothing could survive. And yet, in every one of those places, life has found a way. Not complex life, usually, not plants or animals, but microbes. Tiny, single-celled organisms that have adapted over millions of years to conditions that would kill a human being in seconds. The existence of extremophiles changed how we think about the search for life beyond Earth. For a long time, we assumed that life needed a relatively narrow range of conditions: moderate temperatures, gentle pressures, a certain level of acidity or salinity. But extremophiles showed us that life is more resilient, more adaptable than we had guessed. They opened up the possibility that a planet or a moon does not need to be exactly like Earth to harbor something alive. It might be much hotter, or much colder, or much more acidic, and still, somewhere in a crevice or a subsurface pocket, something might be quietly metabolizing, quietly persisting. The deep-sea hydrothermal vents are a particularly good example. These are places on the ocean floor where superheated water, rich in minerals, pours out of cracks in the Earth's crust. The water can be hundreds of degrees, far above the normal boiling point, kept liquid only by the immense pressure of the ocean above. Sunlight never reaches these depths. The pressure is enough to crush a submarine. And yet, around these vents, whole communities of organisms thrive. Tubeworms, clams, shrimp, and dense mats of bacteria, all living off the chemical energy in the vent fluids. The bacteria at the base of this food chain do not need sunlight. They use a process called chemosynthesis, pulling energy directly from the chemicals dissolved in the hot water. This is a completely different way of powering life than the sunlight-driven photosynthesis that dominates the surface world. It means that a planet could, in theory, be cut off from its star's light entirely and still harbor life around a geothermal vent at the bottom of a dark ocean. That idea has direct implications for moons like Europa and Enceladus, which we will visit later in this journey. The extremophiles in Antarctica tell a different story. There, in the ice, microbes have been found living in tiny veins of liquid water that exist between ice crystals, water so salty it remains liquid at temperatures well below freezing. These organisms metabolize incredibly slowly, barely ticking over, but they are alive. They are not waiting for better conditions. They are adapted to the conditions they have. This tells us that life does not necessarily need a warm, pleasant planet. It might persist in places that are, by our standards, deeply inhospitable. A frozen moon with a subsurface ocean, a dry desert world with occasional seeps of briny water, these are not obviously impossible homes for something microbial. But we should not let the hardiness of life on Earth mislead us into thinking that life is easy. The extremophiles are adapted to extreme conditions, but they are still Earth life. They still use liquid water. They still use carbon-based chemistry. They still rely on DNA or RNA to store genetic information. They are variations on a theme, not a whole new kind of existence. And they do not tell us how likely it is for life to arise in the first place. They only tell us that once life does arise, it can spread into some extraordinarily difficult corners of a planet. The origin of life, the step from non-living chemistry to the first self-replicating system, remains one of the deepest open questions in science. We do not know how it happened on Earth. We have theories, we have laboratory experiments that produce some of the building blocks, but we do not have the full story. And that means we do not know how often that step might occur on other worlds, even if the conditions are right. This is a good moment to pause and let that sink in. We do not know how life started on Earth. That is not a failure of science. It is a reminder of how hard the problem is and how long ago it happened. The earliest evidence we have for life on Earth dates back to around 3.5 to 3.8 billion years ago. That is not long after the planet itself formed and cooled enough to have a solid surface and liquid water. The rocks from that time are rare and heavily altered by the ages since. The first organisms left no fossils in the usual sense, just faint chemical traces, subtle signatures in the ratio of certain isotopes, hints that something living was already at work. Reconstructing the exact steps that led from a prebiotic soup of chemicals to the first cell is like trying to reconstruct a single whispered conversation from echoes that have been bouncing around a canyon for billions of years. So when we go looking for life elsewhere, we carry a certain humility with us. We know what Earth life needs. We know the conditions that allow Earth life to persist. We know some of the chemical signs that Earth life produces. But we do not know if Earth life is the only template, or just one template among many. We search for what we know because we have to start somewhere, but we also try to keep our minds open to the possibility that life, real alien life, might look different from anything we have ever imagined. And yet, for all that openness, the practical search still returns to those three basic requirements: liquid water, an energy source, carbon chemistry. Because every time we have tried to imagine a form of life that does not need at least two of those three things, we run into problems. We cannot figure out how information would be stored and copied without something like carbon's flexible bonding. We cannot figure out how metabolism would work without a solvent to move molecules around. We cannot figure out how the whole system would keep running without an energy gradient of some kind, a flow of energy from a source to a sink, which life can tap into along the way. Maybe our imaginations are just limited. Maybe there is something out there that would rewrite all the textbooks. But until we find it, we work with what we have. There is a quiet comfort in that honesty. It means that the scientists who spend their careers searching for life are not claiming to have all the answers. They are not pretending to know exactly what they are looking for. They are following a reasonable set of clues, the same way you might look for your lost keys under the streetlight, not because you are sure you dropped them there, but because that is where the light is. The difference is that, In this case, the streetlight is getting wider every decade. Our understanding of where life might exist and what it might look like is slowly expanding. The extremophiles expanded it. The discovery of subsurface oceans on icy moons expanded it. The detection of planets around other stars expanded it. Each step widens the circle of light just a little more. So as we move forward in this journey, and we start to visit the actual places where scientists are searching, Mars, Europa, the planets of distant stars, remember this foundation. Remember the 3 requirements, not as rigid rules, but as gentle guidelines. Remember that life on Earth can survive in places we once thought impossible. And remember that the phrase "life as we know it" is not a confession of failure, but an honest statement of where we stand. We are at the beginning of a search that may take generations. We are using the tools and the knowledge we have, knowing full well that both are incomplete. That is not a weakness. That is how all honest inquiry works. The search for life is, in the end, a search for something that we recognize as a reflection of ourselves, not in form, not in appearance, but in the deep, shared quality of being alive. A thing that takes in energy, that maintains itself, that reproduces, that changes over time. A thing that is part of the long, slow thread of evolution, wherever that thread may have started, whether it uses DNA or something entirely different, whether it breathes oxygen or breathes nothing at all, whether it lives in a forest or in a brine-filled crack in the ice of a moon a billion miles away. We are looking for company, in the broadest sense, and the first step in finding company is knowing what it might look like when we see it. So the definition is simple, and it is also incomplete. Life needs water, energy, and carbon. That is what we know, and there is so much more that we do not know. Both things are true. Both things can sit side by side, quietly, without conflict. The not knowing is part of the search, and the search is just beginning. The not knowing is part of the search, and the search is just beginning. But beginning is not quite the right word, because this search has been underway for a very long time. Long before we had telescopes that could detect planets around other stars, long before we had rovers rolling across the surface of Mars, long before we even understood what a galaxy was, people were looking up and wondering. The tools have changed, the knowledge has grown. But the impulse, the quiet, persistent impulse to ask whether we are alone, has been with us for thousands of years. So let us take a slow walk through some of that history. Not a complete history, not a detailed timeline full of dates and names to memorize, but a gentle survey of how the search for life beyond Earth has unfolded over the centuries. Because understanding where we have been, what people once believed, what they got right, and what they got wrong, helps us understand where we are now. It also reminds us that science is not a straight line. It is a winding path, full of corrections and revisions, and those corrections are not signs of failure, they are signs of honesty. Changing your mind when the evidence points in a new direction is one of the most ordinary and necessary parts of doing science. The story goes back much further than you might think. In ancient Greece, more than 2,000 years ago, philosophers were already discussing the possibility of other worlds. Democritus, who lived in the 5th century before the Common Era, proposed that the universe was made of tiny, indivisible particles called atoms, and that there were countless worlds out there, some like ours and some unlike ours. Epicurus, a generation or two later, wrote that there were infinite worlds in the universe, and that it was only natural to assume that some of them would harbor life. These were not scientific claims in the modern sense. They were philosophical arguments, built from logic and intuition rather than observation and measurement. But the core idea, that the Earth might not be unique, that there might be other places where life had taken hold, was already present, already being debated, already keeping thoughtful people awake at night. The ancient Greek atomists were not the only ones. In the same era, thinkers in India and in the Islamic world would later take up similar questions, writing about the plurality of worlds and the possibility of life elsewhere. But we do not need to cover all of that ground. The point is simply that the question is old. It predates modern science. It predates the telescope. It has been part of human thought for as long as we have records of human thought. Now let us skip forward many centuries to a more recent chapter, one that is often told as a cautionary tale in the history of astronomy. It concerns Mars and a man named Giovanni Schiaparelli. Schiaparelli was an Italian astronomer working in the late 19th century. In the year 1877, during a close approach of Mars to Earth, he trained his telescope on the red planet and began mapping what he saw. He observed dark areas and lighter areas. And he observed something else: thin, linear features that seemed to cross the lighter regions, connecting the darker patches. He called these features canali in Italian. That word, canali, means channels. It does not necessarily mean artificial canals built by intelligent beings. It can mean natural channels, grooves, or gullies, but when Schiaparelli's work was translated into English, the word became canals, and that single choice of translation set off a chain of events that would shape the public imagination for decades. The idea of canals on Mars suggested something deliberate. A canal is something you build. It implies engineers, planners, a civilization advanced enough to reshape the surface of an entire planet. The idea caught fire, and the person who did more than anyone else to fuel that fire was an American astronomer named Percival Lowell. Lowell was a wealthy and well-educated man from Boston, with a deep fascination for Mars. He built his own observatory in Flagstaff, Arizona, specifically to study the red planet. And over the years, he produced detailed drawings and writings describing a vast network of canals crisscrossing the Martian surface. He argued that these canals were the work of an intelligent civilization, a dying race desperately channeling water from the polar ice caps to the arid equatorial regions. He published books with titles like Mars as the Abode of Life, and his ideas reached a wide audience. To be clear, Lowell was not a fringe figure shouting from the sidelines. He was a respected member of the scientific community in many ways, and his observatory did real, valuable astronomical work. But his canal theories were, in retrospect, almost certainly a product of optical illusion and the human brain's tendency to see patterns where none exist. When you push a small telescope to the limit of its resolution, faint, blurry features can appear to connect in linear ways. Other astronomers at the time looked through better telescopes under better conditions and saw no canals. They saw a mottled, complex surface, but not the geometric network Lowell described. The scientific consensus, even in Lowell's own time, was skeptical. But the canals of Mars had already taken up residence in the public imagination, and they would stay there well into the 20th century. This story is not told to mock Lowell or Schiaparelli. It is told because it illustrates something gentle and important about how science moves forward. People looked at Mars with the best tools they had. They interpreted what they saw through the lens of their own expectations and hopes. They made mistakes. And then, slowly, as better tools came along and better observations were made, the mistakes were corrected. The canals faded from the maps. The idea of a dying Martian civilization faded from serious scientific discussion. By the time the first spacecraft flew past Mars in the 1960s and sent back images of a cratered, barren surface, the canal hypothesis was already long abandoned by working astronomers. The correction had happened gradually, not in one dramatic moment, but over decades of patient, careful observation. This is how science often works. It does not leap from one absolute truth to another. It gropes forward, sometimes in the wrong direction, and then corrects itself. The correction is not a scandal. It is the method functioning as it should. Every abandoned idea is a step toward a better idea. Every mistake is a piece of the path. And the path from Schiaparelli's channels to the modern rovers on Mars is a path built from thousands of such corrections, large and small. The canal episode also tells us something about human nature. We want to find life. We want to find evidence that we are not alone. That desire is strong enough to shape what we see when we squint through a telescope eyepiece at a distant world. It is something that scientists today are keenly aware of. when a rover on Mars detects a whiff of methane, or when a telescope picks up a hint of oxygen in an exoplanet's atmosphere, the instinctive reaction, the very human reaction, is to hope. But the discipline of science asks for something more. It asks for caution, for verification, for the slow and painstaking elimination of every non-biological explanation before the biological one is accepted. The canal story is a reminder of why that caution is necessary. It is a story about how easy it is to see what we want to see. Before we leave this chapter, it is worth noting that Lowell was not alone in his speculations. The late 19th and early 20th centuries were a fertile time for ideas about life on other worlds. Writers of fiction, H.G. Wells, Edgar Rice Burroughs, and many others filled the public mind with visions of Martians, Venusians, and strange civilizations on distant planets. Newspapers reported on supposed signals from Mars. There was a widespread sense that the solar system might be crowded with intelligent life. This was not a fringe belief. It was, for a time, a fairly mainstream assumption, shared by a surprising number of educated people. And then, slowly, the evidence rolled in. Better telescopes showed Venus to be a hellish world, shrouded in thick clouds of carbon dioxide, with surface temperatures hot enough to melt lead. Mars, seen up close by spacecraft, turned out to be a cold desert, with an atmosphere too thin to support liquid water on its surface for long. The gas giants, Jupiter, Saturn, Uranus, Neptune, had no solid surfaces to stand on. The moon was airless and dead. One by one, the familiar neighbors were crossed off the list of possible homes for complex, surface-dwelling life. The crowded solar system of the early 20th century imagination gave way to the quiet, mostly empty solar system we know today. But even as those doors closed, other doors were opening. The discovery of extremophiles on Earth, which we touched on earlier, showed that life could exist in places we had not thought to look. The discovery of subsurface oceans on moons like Europa and Enceladus suggested that habitable environments might be hidden from view, sealed under miles of ice. And the discovery of planets around other stars, exoplanets as we call them now, opened up an entirely new frontier. The search did not end when the canals turned out to be illusions. It simply changed direction. It became slower, more careful, more methodical, and it extended its reach outward, beyond the familiar planets, to the distant suns that dot the night sky. So the history of looking up is a history of hope, and error, and correction, and renewed hope on a firmer footing. It is a story that spans millennia, from the ancient philosophers sitting under dark Mediterranean skies to the 19th century astronomers squinting through their brass telescopes, to the modern researchers studying data beamed back from spacecraft billions of miles away. The tools have changed beyond recognition. But the question remains exactly the same, and the practice of correcting old ideas, of saying, quietly and without shame, "We were wrong about that, let us try again," remains one of the most honorable things that science can do. There is a certain restfulness in this long view. When you step back and look at the sweep of centuries, the individual debates and discoveries start to blur together into a single, slow rhythm. People look, people wonder, people form ideas. Some of those ideas turn out to be right, many turn out to be wrong. The wrong ones are set aside, and the search continues. No single error is catastrophic. No single discovery is final. The whole enterprise is held together by a shared commitment to looking more carefully tomorrow than we did yesterday. And that commitment has carried us, across thousands of years, from bare-eyed stargazing to spacecraft sailing through the plumes of Enceladus. It is a quiet, persistent thing, this commitment. It does not shout. It does not demand attention. It just keeps going, night after night, generation after generation. And so here we are, at this point in the long arc of the search, lying in the dark, with the same question our ancestors carried to sleep with them. The canals are gone. The Martians of Lowell's imagination are gone. But the real Mars is still there, and we are still studying it, more carefully than ever. The possibility of life has not been disproven. It has been refined, narrowed, and deepened. We know more than we once did about where to look and what to look for. But we are still looking. The search is still open. The sky is still there, waiting for the next generation of eyes to turn toward it. And the closest place those eyes have turned, the first place we have looked most carefully, is also the one that has held our attention the longest: Mars. The fourth planet from the Sun, a world that, even seen with the naked eye, has a reddish tint that sets it apart from the other points of light in the night sky. That color has always stirred something in the human imagination, a suggestion of warmth, of blood, of rust, of something ancient and elemental. It is no accident that Mars is named for the Roman god of war. To the ancients, that red glow seemed fiery, fierce, alive in some way that the steadier, whiter stars were not. Today we know that the red color comes from iron oxide, rust, essentially, in the Martian soil. It is a cold, dry, and harsh world by any measure. The average surface temperature is around -80 degrees Fahrenheit or -60 degrees Celsius. The atmosphere is thin, about 1% as dense as Earth's, and it is made mostly of carbon dioxide. Liquid water cannot last on the surface for long. It would either freeze or boil away almost immediately, depending on the local conditions. The radiation from space, unfiltered by a thick atmosphere or a strong magnetic field, reaches the surface at levels that would be dangerous to any life form we know of that was caught unprotected. This is not a gentle place. It is not an obvious home for anything alive. And yet, Mars has been the central focus of the search for life in our solar system for decades. The reason is simple. There is strong evidence that it was not always this way. Long ago, billions of years ago, Mars was a different kind of world. It had a thicker atmosphere. It had a magnetic field to shield it. And most importantly, it had liquid water, flowing across its surface in rivers, pooling in lakes, maybe even filling a vast ocean in the northern lowlands. We know this not because anyone was there to see it, but because the evidence is written into the rocks and the landscape, still visible today. Orbiting spacecraft have mapped the Martian surface in extraordinary detail. Their cameras have seen features that look exactly like dry riverbeds, winding across the ancient terrain. They have seen the remnants of deltas, where those rivers once fanned out into larger bodies of water. They have seen the shorelines of what appear to be ancient lake basins, and the mineral signatures of rocks that could only have formed in the presence of standing water over long periods of time. These are not ambiguous hints. They are clear, well-documented geological features. The water is gone now, at least from the surface, but the marks it left behind are unmistakable. Mars was once a wet world, and that wet period lasted for hundreds of millions of years, long enough, in theory, for something living to have gotten a foothold. That is the quiet hope that has driven so much of the exploration of Mars. Not that we would find bustling cities or intelligent canal builders. Those ideas were left behind a century ago, but that we might find evidence of past microbial life, preserved in the rocks. Or, just possibly, that we might find some hint that life still clings on in the subsurface, in pockets of briny water deep underground, shielded from the harsh conditions at the surface. This is not a dramatic search. It is a slow, careful, geological search, and it has been carried out by a succession of robotic explorers that have gotten more sophisticated with each generation. The two most advanced of these rovers, as of now, are Curiosity and Perseverance, both sent by NASA. They are car-sized robots, designed to act as mobile field geologists. They drive across the surface, stopping to examine interesting rocks, drilling into them, and analyzing the samples with onboard instruments. Their mission is not to find life directly. They are not carrying microscopes that can watch for wriggling microbes. Instead, they are looking for the chemical and geological signs that life might once have existed there, or that the conditions for life were once present. Curiosity landed in Gale Crater in 2012. Gale Crater was chosen because it contains a mountain of layered sedimentary rock in its center, a formation called Mount Sharp. Those layers are like pages in a book, recording the environmental history of the crater over millions of years. Curiosity has spent more than a decade reading that book, layer by layer, as it slowly climbs the lower slopes of the mountain. What it has found is a story of a changing Mars. The lowest, oldest layers show evidence of a lake that once filled the crater, a lake with fresh, neutral water, not too acidic, not too salty, with the kind of chemistry that we know can support microbial life on Earth. Higher layers show the environment changing, becoming drier, more acidic, less hospitable. It is a record of a world slowly losing its ability to support life on the surface. Perseverance, which landed in 2021, was sent to a different site, Jezero Crater. Jezero was chosen because it contains one of the most well-preserved river deltas on Mars. From orbit, you can see the fan shape of the delta, where an ancient river once spilled into a crater lake, dropping sediment at its mouth. On Earth, deltas are excellent places to look for preserved signs of life, because they trap organic material and bury it quickly in fine-grained mud. The hope is that the same process happened on Mars. Perseverance is exploring that delta, collecting rock samples that will be sealed in tubes and left on the surface for a future mission to retrieve and bring back to Earth. That sample return mission, if it succeeds, will be one of the most significant achievements in the history of planetary science. But it is a long, slow process, and it will take years, probably more than a decade, before those samples are back on Earth and can be studied in the full detail that terrestrial laboratories allow. Both rovers have found organic molecules on Mars. That is an important fact, so let us sit with it for a moment and understand what it means and what it does not mean. An organic molecule, in the scientific sense, is simply a molecule that contains carbon and hydrogen. Organic molecules are the building blocks of life as we know it, but they can also be made by non-living processes. They have been found in meteorites that fell to Earth from space. They have been found in the cold, dark clouds of gas and dust between stars. Finding organic molecules on Mars tells us that the basic chemical ingredients for life are present there. That is interesting. It is worth paying attention to. But it is not the same as finding life. It is not even the same as finding a fossil of a microbe. It is a hint, a clue, a piece of the puzzle, nothing more. To be clear, and this is worth repeating softly but firmly, no confirmed sign of past or present life has been found on Mars. Not by Curiosity, not by Perseverance, not by any of the landers or orbiters that came before them. The search has been going on for decades, with increasingly sophisticated tools, and the answer so far is still the same as it has always been. We do not know yet. The evidence of ancient water is strong. The presence of organic molecules is confirmed. The conditions for life as we know it existed on Mars for a significant stretch of its history. But whether anything actually lived there, whether those conditions ever sparked into something that could be called a living organism, remains an open question. There have been moments in the past when some researchers thought they had found evidence of Martian life, and these moments are worth mentioning because they illustrate how careful the scientific process tries to be. In 1996, a team of scientists announced that a meteorite from Mars, found in Antarctica and known by its catalog number ALH 84001, contained microscopic structures that they interpreted as possible fossilized bacteria. The announcement was big news at the time, but over the following years, the scientific community examined the evidence and found that every single one of the features in the meteorite could be explained by non-biological processes. The structures were too small, the chemistry was ambiguous, and the supposed fossils were not widely accepted as proof of life. The consensus today is that the meteorite does not contain confirmed evidence of Martian biology. It was an honest finding, honestly examined, and the process of scrutiny worked as it should. Science moved on, a little more cautious, a little more knowledgeable. Another episode occurred in the 1970s with the Viking landers. Viking 1 and Viking 2 were the first successful landers on Mars, and they carried experiments designed to test the soil for signs of metabolic activity, the chemical signs of living microbes. One of those experiments, called the labeled release experiment, gave results that some of the scientists involved interpreted as positive. A nutrient solution was added to a soil sample, and gas was released, suggesting something was metabolizing the nutrients. But the other experiments on board, designed to detect organic molecules, found nothing. That contradiction was hard to resolve. If there were living microbes in the soil, why were there no organic molecules to be found? Most scientists eventually concluded that the labeled release results were caused by some non-biological chemical reaction in the Martian soil, perhaps involving peroxides or other reactive compounds. The question was never fully settled to everyone's satisfaction, but the broad view is that Viking did not detect life. It detected a chemical curiosity, something interesting about the soil chemistry, but not biology. Again, the search did not end. It just became more careful. And so, after all of this, after the orbiters, the landers, the rovers, the meteorite debates, the millions of hours of data and analysis, the status of Mars is this. It was once a wet world with conditions that could have supported life as we know it. It is now a cold, dry, and harsh world. Organic molecules are present in the rocks. Some of the chemistry is still not fully understood, but no confirmed evidence of life, past or present, has been found. Not yet. That not yet is important. It is not a promise, it is not a prediction, it is just a statement of openness. The search on Mars is not finished. The rovers are still working. The samples Perseverance is collecting are still waiting to be brought home. There are plans for future missions, including ones that might drill deeper into the subsurface, where liquid water might still exist in aquifers, shielded from the harsh surface. The story of Mars and life is still being written, and the current chapter is simply one of patient, ongoing investigation. There is a quiet beauty in that patience. Mars does not give up its secrets easily. It has been more than a century since Schiaparelli drew his channels, more than a century since Lowell imagined a dying civilization building canals. The reality we have found is both less fanciful and, in its own way, more compelling. A world that was once wet and is now dry. A world that may have had life or may not have. A world that is close enough to touch with our machines, but far enough that every answer requires years of work to obtain. It is the nearest place where the question of life beyond Earth can be asked directly, by a robot arm scratching at a rock. And we are asking it, right now, tonight, as the rovers sit silent in the cold Martian night, waiting for the sun to rise on another day of exploration. So when you think of Mars, think of it not as the home of invaders or canal builders, and not as a solved puzzle, but as a question mark rusting quietly in the dark. It is our closest candidate, our most studied neighbor, and it has not yet told us what we want to know. That is not a disappointment. It is just the pace at which real discovery moves, slowly, carefully, one rock at a time. And while we keep studying Mars, the search has also spread outward, to places that are colder, darker, and farther away, places where the water is not gone but hidden, places that might, in their own strange way, be even better places to look. And while we keep studying Mars, the search has also spread outward, to places that are colder, darker, and farther away, places where the water is not gone but hidden, places that might, in their own strange way, be even better places to look. When you picture the solar system in your mind, you probably picture the sun at the center, and then the planets, arranged in order from the closest to the farthest. Mercury, Venus, Earth, Mars, and then the gas giants, Jupiter, Saturn, Uranus, and Neptune. For a long time, when people thought about the search for life, they thought about the planets. The planets were the obvious places to look. They are large, they are substantial, they have atmospheres and geology and weather. The moons, by contrast, seemed like afterthoughts. Small, cold, dead rocks circling the bigger worlds, interesting only as scenery. But one of the quiet turns in the search for life over the past few decades has been the growing realization that the moons might actually be better candidates than the planets. Not all moons, of course. Most moons are indeed small, cold, and dead, with no atmosphere and no liquid water. But a few of them, in the outer solar system, are turning out to be something very different. They are turning out to be ocean worlds, places where liquid water exists not on the surface, under a sky, but deep underground, sealed beneath thick shells of ice. And that changes everything, because if you have liquid water, and you have a source of energy, and you have the right chemical ingredients, then you have the basic requirements for life as we know it. You do not need sunlight. You do not need a surface you can stand on. You just need those three things, in contact with each other, for long enough that something might begin. The first of these ocean moons we should visit is Europa. Europa is one of the 4 large moons of Jupiter, the ones discovered by Galileo in 1610. It is about the size of our own moon, but it could hardly be more different. From a distance, Europa looks like a cracked white billiard ball. Its surface is made of water ice, and it is one of the smoothest surfaces in the solar system. There are very few craters, which tells you that the surface is relatively young, constantly being resurfaced by some active process. And streaking across that icy surface are long, linear cracks and ridges, some of them thousands of kilometers long, crossing and recrossing each other in patterns that look almost like the seams on a baseball. What lies beneath that icy shell is the reason Europa has become one of the most important targets in the search for life. The evidence, gathered over decades by multiple spacecraft, points strongly toward a global ocean of liquid water hidden under the ice. We do not know exactly how thick the ice shell is. Estimates range from a few kilometers to tens of kilometers, but beneath that ice, the ocean could be as deep as 100 kilometers or more. That means Europa could have more liquid water than all of Earth's oceans combined. Think about that for a moment. A moon, smaller than our own, circling Jupiter nearly 500 million miles from the Sun, holding more water than the entire Earth. It is a strange and wonderful thing to contemplate in the dark. The evidence for this ocean comes from several different sources. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, made multiple close flybys of Europa. It measured the moon's magnetic field and found that it was being influenced by a conducting layer beneath the surface, something salty and fluid, like an ocean. It also took detailed images of the surface, which showed features that look very much like icebergs that have broken apart and drifted before refreezing into new positions. That kind of chaotic terrain is exactly what you would expect if there were a liquid layer beneath a brittle ice shell. More recently, the Hubble Space Telescope has observed what appear to be plumes of water vapor erupting from Europa's surface, rising high above the ice before falling back down. If those plumes are real, and the evidence is strong but not yet completely definitive, they offer a way to sample the ocean without having to drill through kilometers of ice. Now let us move farther out, to Saturn. Saturn also has a large and varied collection of moons, and one of them has captured the attention of scientists in a way that rivals Europa. That moon is called Enceladus. Enceladus is much smaller than Europa, only about 500 kilometers across, which is roughly the width of the state of Arizona. It is so small that, for a long time, nobody expected it to be geologically interesting at all. Small bodies cool quickly and become inactive. That was the conventional thinking. Enceladus proved that thinking wrong. The Cassini spacecraft arrived at Saturn in 2004 and spent 13 years exploring the planet, its rings, and its moons. When Cassini turned its instruments toward Enceladus, it found something nobody had predicted. The moon's south polar region was warm, warmer than it should have been, and it was venting material into space. Huge plumes of water vapor, mixed with ice particles and other chemicals, were shooting out of cracks in the ice at hundreds of meters per second. Those cracks, sometimes called tiger stripes, because of their appearance in images, are fissures in the ice shell, where the ocean beneath is leaking into space. Cassini did more than just photograph the plumes. It flew directly through them multiple times and sampled them with onboard instruments. What it found was remarkable. The plumes contain water vapor, of course, but they also contain molecular hydrogen. They contain organic molecules, simple carbon-based compounds. They contain salts, similar to the salts you would find in Earth's oceans. And they contain tiny grains of silica, which on Earth form in hot water near hydrothermal vents. All of this together paints a picture of an ocean that is not just a cold, sterile body of water, but an active, dynamic environment, with chemical reactions taking place between the water and a rocky seafloor. The presence of hydrogen in particular is important, because on Earth, hydrogen is a key energy source for microbes that live around hydrothermal vents. Those microbes use a process called methanogenesis to combine hydrogen with carbon dioxide, producing methane and extracting energy in the process. The fact that hydrogen is present in the plumes of Enceladus suggests that similar chemical pathways might be available there. But we must be careful here. Finding the ingredients for life is not the same as finding life. The organic molecules in the plumes of Enceladus are interesting, but they are not proof of biology. They could be produced by non-living chemical reactions. The hydrogen is interesting for the same reason. The warmth of the South Pole is interesting because it implies a heat source, probably tidal heating, where the gravitational pull of Saturn and other moons flexes and stretches Enceladus, generating friction and heat in its interior. All of these things together make Enceladus one of the most promising places to look for life in the solar system, but they do not yet tell us that life is there. That distinction is important, and it is worth repeating. Enceladus has the right conditions for life as we know it. It has liquid water, an energy source, and organic chemistry. What it does not have, what neither Europa nor Enceladus has, is a confirmed detection of life itself. No mission has yet landed on either moon. No probe has drilled through the ice and sampled the ocean directly. The plumes of Enceladus are the closest we have come to tasting an alien ocean, and even those samples were gathered during brief, high-speed flybys, not by a dedicated lander or submarine. We are still at the very beginning of exploring these places. The data we have is tantalizing, but it is not conclusive. And in science, the distance between tantalizing and conclusive can be very long indeed. There are other icy moons worth mentioning, though they are less well studied. Titan, another moon of Saturn, has a thick atmosphere and liquid lakes on its surface, but those lakes are made of methane and ethane, not water. Titan is fascinating for its own reasons, and some scientists wonder whether a very different kind of life, one not based on water at all, could exist there. But that is a more speculative idea, and for now, the focus of the water-based search remains on Europa and Enceladus. Ganymede, another moon of Jupiter, is also thought to have a subsurface ocean, and it has its own mission planned. There may be other ocean moons out there, around Uranus or Neptune, that we simply have not studied closely enough yet. The outer solar system is full of ice, and where there is ice and heat, there can be water. And where there is water, there is at least the possibility of something more. What makes these icy moons so compelling, in the quiet logic of the search, is that they offer something Mars cannot. Mars had liquid water on its surface, billions of years ago, but that water is mostly gone now. If life ever existed on Mars, it may be long extinct, preserved only as fossils or chemical traces. The icy moons, by contrast, still have their oceans. They are still warm inside. Their environments are still active, still changing, still potentially capable of supporting living organisms right now. If you wanted to find life that is alive today, rather than a record of life that was alive long ago, the icy moons might be the best bet in the solar system. But they are also much harder to reach. Mars is relatively close. A spacecraft can get there in about 7 months. The journey to Jupiter takes years. The journey to Saturn takes even longer. The outer solar system is a realm of long travel times and faint sunlight, where spacecraft have to operate on very limited power, far from the sun that feeds their solar panels. The missions to these moons are expensive, complicated, and slow. They require decades of planning and patience. The people who design them often do so knowing that the most important data will arrive long after they have retired, or even after they have died. This is not a field for people who need quick results. It is a field for people who are comfortable planting trees whose shade they will never sit in. And so, as with Mars, we sit with an open question. Europa has an ocean. Enceladus has an ocean. Those oceans are salty, and they are in contact with rock, and they contain organic molecules and chemical energy sources. They are, by every measure we can apply from a distance, habitable environments. But habitability is not the same as inhabited. A place can be perfectly suitable for life and still be sterile. We do not know which is true for these moons. We do not know if the spark that started life on Earth was a common occurrence or a rare one. We do not know if it happened on Europa or on Enceladus or on neither. What we do know is that these moons exist, and that they are waiting, and that missions are being planned to study them more closely. The European Space Agency's JUICE mission, that stands for Jupiter Icy Moons Explorer, is on its way to the Jupiter system now. NASA's Europa Clipper mission is also on its way, specifically designed to study Europa and its ocean. Both of these missions will make multiple close flybys, gathering data about the ice shells, the subsurface oceans, and the chemistry of these worlds. They will not drill through the ice. They will not send a submarine into the deep, but they will lay the groundwork for whatever comes next. They will help us understand where to look and how to look, and what we might find when we finally do break through the ice and touch the water beneath. So as you drift further into rest, picture these moons in your mind. Picture Europa, pale and cracked, circling Jupiter in the dark. Picture Enceladus, tiny and bright, its plumes glittering in the faint light of a distant sun. Picture the oceans beneath their icy crusts, dark and cold and deep, stirred by currents and warmed by vents on the seafloor. No one has ever seen these oceans. No camera has ever captured their depths. They exist only as a deduction, a conclusion drawn from magnetic fields and gravity measurements and the chemistry of plumes. And yet they are as real as any ocean on Earth. They have tides, they have chemistry, they have heat, and they may, or may not, have something alive moving through their waters. The question is open, the night is long, and the moons keep their secrets beneath the ice. The question is open, the night is long, and the moons keep their secrets beneath the ice. Now, before we travel any farther outward, before we leave the familiar territory of our own solar system and venture into the realm of planets circling other stars, there is a concept we should slow down and sit with for a while. It is a concept that gets used a lot in conversations about the search for life, and it is often used too loosely. It is the idea of the habitable zone. You may have heard this term before. You may have heard it called by its informal nickname, the Goldilocks zone. But what does it actually mean? And just as importantly, what does it not mean? The habitable zone is a way of describing a certain distance from a star. It is the range of distances where, in theory, a planet with the right kind of atmosphere could have liquid water on its surface. Not too close to the star, where the heat would boil the water away. Not too far from the star, where the cold would freeze it solid. Just the right distance, where the temperature could be just right for liquid water to pool and flow and persist over long periods of time. That is the simple idea. It is a Goldilocks idea, not too hot, not too cold, but somewhere in the middle, where conditions could be, in this one specific sense, just right. But notice the careful language in that description. The habitable zone is about where liquid water could exist on a planet's surface, given the right atmosphere. It is not a guarantee. It is not a promise. It is not a label that means a planet is definitely habitable. It is a starting point, a first filter, a way of sorting through the vast number of worlds out there and picking out the ones that are worth a closer look. Being in the habitable zone does not mean a planet has water. It does not mean a planet has an atmosphere. It does not mean a planet has life. It only means that the temperature range, based on the star's brightness and the planet's distance, is such that liquid water is not ruled out by basic physics. This is important to understand because the term habitable zone sounds more definitive than it really is. The word habitable suggests that a place is fit to live in, but a planet can be in the habitable zone and still be completely inhospitable. It could be a bare rock with no atmosphere at all. It could be a Venus-like world with a thick, crushing atmosphere of carbon dioxide and surface temperatures hot enough to melt lead. It could be a tiny world with gravity too weak to hold on to any air. It could be a water world with an ocean so deep that the pressure at the bottom turns the water into a strange, hot ice, sealing off any contact with the rocky minerals that life might need. It is a zone of possibility, and possibility is a much softer, more cautious word. Our own solar system provides a useful example. Let us look at 3 planets: Venus, Earth, and Mars. All 3 of these planets orbit within or very near the habitable zone of our Sun. The Sun's habitable zone, as calculated by most models, stretches from roughly the orbit of Venus to roughly the orbit of Mars. Earth sits comfortably in the middle, and Earth, as we know, has liquid water on its surface, and it has life. That fits the habitable zone concept nicely. But then look at Venus. Venus is nearly the same size as Earth. It orbits closer to the Sun, but not enormously closer. It is near the inner edge of the habitable zone, not far beyond it. And yet Venus is, by any reasonable measure, a hellscape. Its surface temperature is around 860 degrees Fahrenheit, or 460 degrees Celsius, hot enough to melt tin and lead. Its atmosphere is 90 times thicker than Earth's, composed almost entirely of carbon dioxide, with clouds of sulfuric acid. No liquid water exists on its surface. No life as we know it could survive there. Venus is technically inside the habitable zone, but it is not habitable. The habitable zone concept said maybe, and the reality of Venus said no. Then consider Mars. Mars orbits near the outer edge of the Sun's habitable zone. It is farther from the Sun than Earth, and so it receives less heat. And Mars does have evidence of ancient liquid water, as we discussed earlier. But today, its surface is dry and frozen. The atmosphere is too thin to keep water liquid for long. Mars is in the habitable zone, but just barely, and whatever habitability it once had has mostly slipped away. So of the 3 planets in or near our Sun's habitable zone, one is a living world, one is a dead inferno, and one is a frozen desert that may have once been wetter. That is a 1 in 3 success rate, and even that one success is the very planet we are standing on. We have no other confirmed successes to point to. The habitable zone, then, is a rough guide, not a definitive label. It tells you something about the temperature, if the planet has an atmosphere something like Earth's. But planets do not all have atmospheres like Earth's. An atmosphere can trap heat through the greenhouse effect, warming a planet well beyond what the distance from the star would suggest. Or an atmosphere can be thin and weak, allowing heat to escape and leaving the surface cold. The actual surface temperature of a planet depends on a complicated interaction between the star's light, the planet's reflectivity, the composition and thickness of its atmosphere, and even things like the planet's rotation rate and the presence of oceans. The habitable zone simplifies all of that into a single distance range. It is useful for making lists of interesting planets. It is not useful for making firm claims about whether those planets are actually habitable. There is another layer of subtlety here. When we talk about the habitable zone, we are almost always talking about the surface of a planet. The idea is rooted in the notion of a planet like Earth, with continents and oceans and an atmosphere basking in the light of its star. But as we have seen with the icy moons, a world does not need surface liquid water to be a candidate for life. Europa and Enceladus are far, far outside the Sun's habitable zone. They orbit in the cold reaches of the outer solar system, where sunlight is faint and surface temperatures are hundreds of degrees below freezing. And yet, they have liquid water, hidden deep beneath their ice. Their water is kept liquid not by starlight, but by tidal heating. the constant gravitational kneading they receive from their parent planets and sibling moons. This kind of subsurface ocean does not care about the habitable zone at all. The habitable zone is about surface water under a star's light. It says nothing about subsurface water kept warm by internal heat. So when you hear about a planet in the habitable zone of another star, remember that it is only one kind of possibility. There may be other kinds of habitable environments, like the oceans of icy moons, that the habitable zone concept does not even begin to address. And yet, for all its limitations, the habitable zone remains a useful concept. It gives us a place to start. The galaxy contains hundreds of billions of stars, and those stars host an even greater number of planets. We cannot study them all in detail. We need a way to prioritize, to pick out the ones that are most worth spending our limited telescope time on. The habitable zone is that first filter. If a planet is in the habitable zone, it is worth checking for an atmosphere. If it has an atmosphere, it is worth checking for water vapor and other interesting gases. If it has those gases, it is worth studying more closely, looking for the chemical fingerprints that might suggest something biological is going on. Each step narrows the list. Each step brings us closer to an answer, and the habitable zone is step one. The concept of the habitable zone has also changed over time as our understanding of planets and stars has improved. The classical habitable zone, the one most often discussed, is based on a planet with an atmosphere of nitrogen, carbon dioxide, and water vapor, something broadly Earth-like. But scientists have also proposed other kinds of habitable zones. There is the idea of a habitable zone for life as we know it, which is the classic one. Then there is the habitable zone for complex life, which might be narrower, because complex organisms may need more specific conditions than simple microbes. There is even speculation about habitable zones around different types of stars. Red dwarfs, for example, have habitable zones much closer in than our suns, and planets there would be tidally locked, with one side always facing the star and one side always in darkness. Whether such planets can actually support life is an open and actively debated question. The point of all this is not to memorize the different types of habitable zones. The point is to understand that the phrase itself is a tool, not a verdict. It is a way of saying, this place is worth a closer look, not, this place is a second Earth. When you hear that astronomers have found a planet in the habitable zone of its star, what you are hearing is that the planet is at the right distance for surface liquid water to be possible, given the right atmosphere. That is all. It is a clue, a lead, a reason to keep looking. It is not a discovery of a habitable world. It is a discovery of a world that might be habitable if many other conditions are also met. And those other conditions are numerous. A planet in the habitable zone still needs the right chemical ingredients. It needs a stable climate over long periods. It needs a magnetic field to shield it from stellar radiation, or at least an atmosphere thick enough to absorb that radiation. It needs a surface with the right minerals to support prebiotic chemistry. It needs a history of impacts and geological activity that delivers energy and nutrients without sterilizing the surface too often. The list goes on. The habitable zone is just one item on that list. It is an important item, but it is not the only one. So as we prepare to move outward to the exoplanets, the planets around other stars, hold this idea gently. The habitable zone is a starting point. It is a way of narrowing down the search. It is not a guarantee of water or of life or of anything at all. It is a possibility, not a promise. And in a universe as vast and as varied as ours, possibilities are worth paying attention to. They are worth studying. They are worth the slow, patient work of gathering data and testing hypotheses. But they are not conclusions. The conclusion, if it ever comes, will come later, after years of careful observation and analysis. And until then, the habitable zone remains what it has always been, a quiet, tentative circle drawn around a star, marking the region where, if things were just right, water might flow and something might grow. That is enough for now. That is enough to guide the next steps of the journey. The concept is simple at its core. even if the details are complex. A star has a region around it where the temperature is, in principle, right for liquid water on a planetary surface. That region is the habitable zone. Planets in that zone are interesting. Planets outside that zone might still be interesting for other reasons, as the icy moons have shown. But the habitable zone gives us a place to point our telescopes, a set of targets to study. And in the long, slow work of searching for life, having a good set of targets is half the battle. So let the idea rest in your mind as you rest. The habitable zone, the Goldilocks zone. Not too hot, not too cold. A circle of possibility, not a stamp of approval. A way of saying maybe, in a galaxy full of maybes. And with that idea settled, we can now turn our attention to the stars themselves, and to the worlds we have found orbiting them. Worlds that are real, and numerous, and waiting to be understood. And with that idea settled, we can now turn our attention to the stars themselves, and to the worlds we have found orbiting them, worlds that are real and numerous, and waiting to be understood. For most of human history, the planets of our own solar system were the only planets we knew about. Mercury, Venus, Earth, Mars, Jupiter, Saturn, these were the sum total of known worlds. A few astronomers suspected that there might be planets around other stars, but there was no way to confirm it. The distances were too vast. A planet, unlike a star, does not shine with its own light. It is a tiny, dim speck lost in the glare of its parent sun. Trying to see one from Earth was like trying to see a firefly hovering next to a searchlight from 100 miles away. For a long time, the question of whether other stars had planets was exactly that, a question, with no clear path to an answer. That changed in the 1990s. The first confirmed detection of a planet orbiting a star like our own Sun came in 1995, when astronomers Michel Mayor and Didier Queloz found a world circling the star 51 Pegasi, about 50 light-years from Earth. That planet was not like anything in our solar system. It was a gas giant, similar in mass to Jupiter, but it orbited incredibly close to its star, completing a full orbit in just over 4 Earth days. It was the first of what we now call hot Jupiters, large planets on very short orbits, blasted by their star's heat. It was not a candidate for life, but its discovery proved that planets around other stars were detectable, and once that door was opened, it stayed open. In the decades since, astronomers have found thousands of these planets. They are called exoplanets. Exo meaning outside, so planets outside our solar system. The number of confirmed exoplanets now sits in the thousands, and that number grows steadily as telescopes keep watching and data keeps accumulating. There are thousands more candidate planets, signals that look like planets but have not yet been confirmed by independent observations. The total number of exoplanets in our galaxy is almost certainly in the billions. For every star you can see in the night sky, there is a good chance that at least one planet is circling it, and probably more. But how do we find them? How do you detect something so small, so far away, that it produces no light of its own? The methods are, in their own way, beautifully simple. They do not involve photographing the planet directly, at least not in most cases. Instead, they involve watching the star and looking for tiny, subtle changes, changes in brightness, changes in motion, that betray the presence of something orbiting around it. There are 2 main methods that have found the most exoplanets so far, and understanding them does not require any special knowledge. They are ideas you can hold in your mind without effort. The first method is called the transit method. Imagine you are standing on a hill, looking at a lighthouse far in the distance. The lighthouse beam is steady and bright. Now imagine that a bird flies across the face of the lighthouse, passing between you and the light. For just a moment, the light dims by a tiny amount, not turning off, just getting a little bit fainter, and then it returns to full brightness. That dimming tells you that something passed in front of the light. The transit method works on exactly that principle. A telescope watches a star, measuring its brightness very precisely over time. If a planet passes in front of that star, if it transits, moving across the star's face from our point of view, the star's light will dip by a tiny fraction. The amount of the dip tells you something about the size of the planet. A big planet blocks more light, a small planet blocks less. The time between dips tells you the length of the planet's year, how long it takes to complete one orbit. If you watch long enough, you can build up a picture of the planet's size, its orbit, and even some clues about its temperature. This sounds simple, and in principle it is, but in practice, the dips are very small. An Earth-sized planet passing in front of a Sun-sized star blocks about 1/10,000th of the star's light. That is a change so tiny that it requires instruments of extraordinary sensitivity and a lot of patience. The star might vary in brightness for other reasons too: star spots, flares, instrumental noise. Teasing out the signal of a transiting planet from all that noise is delicate work, but it can be done, and it has been done, thousands of times. The second major method is called the radial velocity method, or sometimes the wobble method. This one is a little less intuitive, but it is just as elegant. We tend to think of a planet orbiting a star as if the star is fixed and the planet goes around it. But in reality, gravity works both ways. The star pulls on the planet, and the planet pulls on the star. The star is much, much more massive, so it does not move very much. But it does move, just a little. It wobbles, very slightly, in a tiny circle or ellipse that mirrors the planet's orbit. The radial velocity method detects that wobble by looking at the star's light. As the star wobbles toward us, its light shifts slightly toward the blue end of the spectrum. As it wobbles away from us, the light shifts slightly toward the red. This is the same Doppler effect that makes a siren sound higher as it approaches and lower as it recedes. By measuring these tiny shifts in the star's light, astronomers can infer the presence of a planet, and they can estimate its mass. A heavier planet produces a bigger wobble. A lighter planet produces a smaller one. The transit method and the radial velocity method complement each other nicely. The transit method tells you the planet's size, how much of the star's light it blocks. The radial velocity method tells you the planet's mass, how hard it pulls on the star. Together, they tell you the planet's density, which is a clue about what it is made of. A planet with the size of Earth and the mass of Earth is likely rocky. A planet with a large size but a low density is likely a gas giant. A planet with an intermediate density might be a water world. Each piece of information narrows down the possibilities. The spacecraft that did more than any other to open the floodgates of exoplanet discovery was the Kepler Space Telescope, launched by NASA in 2009. Kepler was designed to stare at a single patch of sky, near the constellation Cygnus, for years on end. It monitored the brightness of roughly 150,000 stars, looking for the telltale dips that would indicate transiting planets. And it found them by the thousands. Kepler showed that planets are not rare, they are common. They are the rule, not the exception. It showed that small, rocky planets are particularly abundant, at least in the size range somewhat larger than Earth but smaller than Neptune. It showed that multi-planet systems are normal, with stars often hosting several planets orbiting in flat, orderly planes, like our own solar system. It showed that the galaxy is, in a very real sense, full of worlds. Kepler's mission ended in 2018, but its data is still being analyzed, and its legacy is immense. Other telescopes, both on the ground and in space, have continued the work. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, is surveying the whole sky, looking for exoplanets around the nearest and brightest stars, the ones that are easiest to study in detail, with follow-up observations. The James Webb Space Telescope, which we will talk about more in the next section, is now taking those closest and brightest targets and studying their atmospheres. The search has moved from simply finding exoplanets to trying to understand what they are like. It is worth pausing here to absorb the scale of what has happened. When you were born, depending on when exactly that was, it is quite possible that no planets outside our solar system were known. Now we know of thousands. We know that the night sky, which looks so quiet and so still, is actually teeming with worlds. Every point of light you can see, and countless more that are too faint for the naked eye, is a star that might have its own system of planets. Some of those planets are gas giants, larger than Jupiter. Some are ice giants, like Neptune. Some are rocky, like Earth and Mars, orbiting at distances where liquid water could, in theory, exist on their surfaces. The galaxy has turned out to be not a sparse desert, but a crowded archipelago of worlds, and we are only just beginning to map its shores. Of course, finding a planet and knowing whether it might host life are two very different things. The transit method and the radial velocity method give us sizes, masses, orbits, and sometimes densities. They can tell us whether a planet is in its star's habitable zone, but they cannot, by themselves, tell us whether a planet has an atmosphere or what that atmosphere is made of, or whether the planet is actually habitable. For that, we need a different set of tools. We need to be able to read the light from the planet itself, to pick it apart and look for the signatures of gases, the fingerprints of chemistry, the hints of something that might be alive. That is the next step in the journey, and it is a step we are taking right now, with telescopes that are pushing the limits of what we can see and measure. The thousands of exoplanets are a catalogue of possibilities. The next phase of the search is to turn those possibilities into something more, to move from "this planet exists" to "this planet has an atmosphere," and then, perhaps, to "this planet's atmosphere has signs that are, on Earth, associated with life." It is a slow, methodical process. It will not yield answers overnight, but it is underway, and it is one of the most extraordinary quiet endeavors of our time. For now, as you rest, just hold on to the simple fact that the stars have planets, lots of them, more than you could count in a lifetime, and among those planets there are some, we do not yet know how many, that are rocky and temperate and orbiting at the right distance for liquid water to be possible. They are out there, right now, circling their stars in the dark. Some of them are transiting their stars as you breathe in and out, casting tiny shadows that no human eye has ever seen. The data is being gathered, the light is being collected, the search is moving forward, one observation at a time. And the next part of that search involves learning to read the light itself, to pull it apart into its component colors, and look for the subtle marks that a living world might leave on the spectrum of its star. That technique has a name, and we will come to it soon. But for now, just the stars and their planets, and the quiet knowledge that the galaxy is far richer than we once imagined. And the next part of that search involves learning to read the light itself, to pull it apart into its component colors, and look for the subtle marks that a living world might leave on the spectrum of its star. That technique has a name, and we will come to it now. We have found the planets. Thousands of them. We know their sizes, we know their masses, we know how long their years are. We know which ones are in the habitable zones of their stars. But that is still surface-level information. It tells us where to look, but it does not tell us what we are looking at. The next step, the step that moves us from cataloging worlds to understanding them, is to study their atmospheres. To do that, we need a way to read the chemical makeup of a planet's air from trillions of miles away, and the tool that makes that possible is called spectroscopy. The word spectroscopy sounds technical, but the idea behind it is something you already understand, even if you have never thought about it in these terms. Light carries information. When sunlight passes through a glass prism, it splits into a rainbow, a band of colors from red to violet. That band of colors is called a spectrum, and that simple rainbow, if you look at it closely enough, contains a hidden message. Certain colors, certain very specific shades of red or yellow or green, can be missing from the rainbow, or they can be brighter than expected. These missing or brightened bands are like fingerprints. They are caused by different kinds of atoms and molecules, absorbing or emitting light at very particular wavelengths. Sodium, for example, absorbs light at two very specific shades of yellow. Hydrogen absorbs light at a specific shade of red, and another in the blue-green, and so on through the spectrum. Every element, every molecule, has its own unique pattern of fingerprints in the light. Give a physicist a detailed enough spectrum, and they can tell you what the light passed through on its way to the telescope. This is how we know what stars are made of. We point a telescope at a star, split its light into a spectrum, and read the fingerprints. Hydrogen lines, helium lines, traces of iron, calcium, oxygen, carbon. The star tells us its composition, and we read it from millions or billions of miles away. The same principle applies to planets. If a planet passes in front of its star, if it transits, a tiny fraction of the starlight passes through the planet's atmosphere on its way to us. That light, just before it leaves the planet's outer edge, filters through the gases that make up the planet's air, and those gases leave their fingerprints on the spectrum. By comparing the spectrum of the star when the planet is not in front of it to the spectrum when the planet is in front of it, astronomers can subtract one from the other and isolate the tiny signal of the planet's atmosphere. It is an exquisitely delicate measurement. The signal from the atmosphere is often 1 part in 10,000, or 1 part in 100,000, compared to the star's light. But it can be done. It has been done. The telescope that is doing this work more powerfully than any before, it is the James Webb Space Telescope. Launched in December of 2021, Webb is the most ambitious space observatory ever built. It operates not in visible light, like our eyes and most traditional telescopes, but primarily in the infrared, the part of the spectrum just beyond the red end of the rainbow. Infrared light is particularly useful for studying exoplanet atmospheres because many of the molecules we care about, water, carbon dioxide, methane, oxygen, have strong fingerprints in the infrared. Webb's large mirror, over 6.5 meters across, gathers enough light to make these faint atmospheric signals measurable. Its instruments can split that light into spectra of exquisite detail. It is, in a very real sense, a machine for reading the chemical signatures of distant worlds. Webb has already begun this work. It has observed the atmospheres of several exoplanets, mostly hot gas giants that are easier to measure because they are large and their atmospheres are puffed up by the heat. But it is also turning its attention to smaller, cooler worlds, planets that are closer in size and temperature to Earth. The goal, over the coming years, is to build up a catalog of exoplanet atmospheres, to see what is out there, to understand the range of possibilities. Some planets will have thick atmospheres dominated by hydrogen and helium. Some will have atmospheres of carbon dioxide, like Venus and Mars. Some may have water vapor, indicating the presence of liquid water on the surface or in the clouds. And some perhaps will have gases that are harder to explain, without invoking the presence of life. That brings us to an important term, biosignature. A biosignature is simply a gas, or a combination of gases, that on Earth is strongly associated with the activity of living things. The classic example is oxygen, in large amounts, alongside a gas like methane. On Earth, oxygen makes up about 21% of our atmosphere. That oxygen is almost entirely produced by living things, by plants, algae, and cyanobacteria that use photosynthesis to split water molecules and release oxygen as a waste product. Without life constantly replenishing it, oxygen is a reactive gas. It does not stay free in an atmosphere for long on geological timescales. It binds with rocks, it oxidizes minerals, it dissolves in the oceans. The fact that our atmosphere is so rich in oxygen is a direct consequence of the living things that produce it. Methane, on the other hand, is produced by a variety of sources, some biological and some not. On Earth, a significant fraction of methane comes from microbes, especially those living in wetlands and in the guts of animals. Methane is also broken down relatively quickly in an oxygen-rich atmosphere. So if you were to look at Earth from a distance and see both oxygen and methane present in the atmosphere at the same time, that combination would be a biosignature. It would tell you that something is actively producing both gases, and that something is very likely biological. No known non-biological process can sustain large amounts of oxygen and methane together in an atmosphere for long periods. They react with each other, so seeing them side by side implies continuous resupply. But here is where we must be careful. The idea of a biosignature is powerful, but it is not foolproof. Finding oxygen and methane together on an exoplanet would be a big deal. It would be front-page news. It would be the strongest hint of life we have ever found beyond Earth. But it would not be proof. There might be non-biological processes we have not thought of that could produce the same combination. There might be exotic photochemistry, or unusual geological activity, or some other mechanism that mimics the biosignature. Science is full of examples where a seemingly definitive sign turned out to have a mundane explanation. The canals of Mars are one such cautionary tale. The claimed fossil microbes in the Martian meteorite are another. The history of the search for life is a history of being careful, of checking and rechecking, of insisting on extraordinary evidence for extraordinary claims. And so when astronomers talk about biosignatures, they use the term with deliberate modesty. A biosignature is not a detection of life. It is a clue. It is a reason to look more closely. It is a flag that says, this planet is worth more telescope time. Confirming that a biosignature is truly biological would require a long chain of evidence, multiple independent measurements, a deep understanding of the planet's geology and chemistry, and probably the elimination of every conceivable non-biological alternative. That process could take decades. It could take generations. The first claimed biosignature on an exoplanet will almost certainly be debated for years before any consensus emerges, and even then, some doubt will likely remain. Short of actually sending a probe to the planet, which is impossible with current technology for all but the very nearest stars, there will always be some level of uncertainty. This is not a pessimistic view. It is an honest one. The search for life is hard. It is hard in the solar system, where we can send rovers and landers and actually touch the rocks. It is harder still across interstellar distances, where all we have is light. But the fact that it is hard does not make it impossible. It just makes it slow. And slow, as we have been saying throughout this journey, is the pace at which real understanding unfolds. The James Webb Space Telescope is not the only tool for this work, but it is the most capable one we have right now. Ground-based telescopes with very large mirrors, like the European Southern Observatory's Very Large Telescope in Chile, are also doing atmospheric spectroscopy, particularly for planets around the smallest, coolest stars. Future telescopes, not yet built, are being designed with the explicit goal of finding and characterizing Earth-like planets. The search is scaling up, generation by generation. The first exoplanet atmosphere was detected in the early 2000s, around a hot Jupiter. Now, barely 2 decades later, we are measuring the atmospheres of planets not much larger than Earth. The progress is steady, and it is pointing in one direction, toward the day when we will have a spectrum of a truly Earth-like planet, in the habitable zone of its star, and we will see what its air is made of. What will we find? We do not know. That is the whole point. Maybe we will find that Earth-like atmospheres are rare. Maybe we will find that they are common but sterile. Maybe we will find a planet with an atmosphere that looks, in its chemical details, very much like our own, oxygen-rich, with traces of methane and water vapor and other gases that speak to an active biosphere. Or maybe we will find something completely unexpected, an atmosphere that does not fit any of our models, a chemical signature that we cannot explain with either geology or biology. That would be just as interesting, in its own way, as finding a biosignature. It would remind us that the universe is more creative than our theories, and that we still have much to learn. For now, though, we are at the beginning of this phase of the search. The data is rolling in, slowly. Each spectrum takes hours of telescope time, and the most interesting targets are faint and difficult. The analysis takes months. The results trickle out in scientific papers, each one adding a small piece to the puzzle. This is not a field for people who want instant answers. It is a field for people who are content to work on a problem that will outlive them. And for the rest of us, it is a field that invites a certain kind of patience, a willingness to sit with open questions and let them be open. So as you rest, Think of the light. Think of the starlight that has traveled for decades or centuries or millennia, carrying the fingerprints of planets we will never visit. Think of the telescopes, sitting in the cold of space or on high mountaintops, patiently gathering that light and breaking it into rainbows. Think of the researchers looking at those rainbows and picking out the tiny dips and peaks that correspond to water, to carbon dioxide, to methane, to oxygen. And think of the moment, if it ever comes, when one of those rainbows shows a pattern that looks, to the best of our knowledge, like the signature of a living world. That moment has not arrived yet. It may not arrive in our lifetimes, but the search for it is underway, and that search is one of the quiet wonders of our time. That moment has not arrived yet. It may not arrive in our lifetimes, but the search for it is underway, and that search is one of the quiet wonders of our time. Now, with all of these tools and concepts in mind, the habitable zone, the transit method, the reading of atmospheres through spectroscopy, it is time to visit one specific, real place. One star system that has become, in the last few years, a kind of touchstone for the search. It is not the closest system to us, and it is not the most Earth-like in every detail, but it is the one that has captured the most attention, because it offers something no other system we know of does. 7 rocky planets, all roughly the size of Earth, all orbiting a single small star, and several of them in or near the habitable zone. That system is called TRAPPIST-1. The name TRAPPIST comes from the telescope that discovered the first planets there, a ground-based telescope in Chile called the Transiting Planets and Planetesimals Small Telescope. That is a mouthful, but the acronym TRAPPIST is easy to remember, and it has a certain quiet charm. The star itself, TRAPPIST-1, is nothing like our Sun. It is what astronomers call a red dwarf, also known as an M-dwarf. These are the smallest and coolest kind of true star. TRAPPIST-1 has only about 8% of the mass of our Sun, and it is much, much dimmer. If you could stand on one of its planets and look up, the star would appear larger in the sky than our Sun does, but it would give off far less light. It would glow a deep, reddish orange, like the embers of a dying fire. The planets huddle close to it for warmth, all 7 of them orbiting within a distance that, in our solar system, would fit inside the orbit of Mercury. TRAPPIST-1 is about 40 light-years from Earth. That is a number that sounds large, and in human terms it is unimaginably vast, but in galactic terms it is practically next door. The Milky Way galaxy is roughly 100,000 light-years across. 40 light-years is a tiny fraction of that. It is close enough that the system is a prime target for detailed study with our best telescopes. The light from TRAPPIST-1 left that star 40 years ago and has been traveling through space ever since, and when it arrives at our telescopes, it carries information about the planets that orbit there. The system was revealed in stages. The first 3 planets were announced in 2016. Then, in 2017, the full picture came into focus. 7 planets, all of them roughly Earth-sized, all of them likely rocky. They are labeled with letters, TRAPPIST-1b, the closest to the star, then 1c, 1d, 1e, 1f, 1g, and 1h, the farthest out. The letters were assigned in order of discovery, not in order of distance, but they are often listed in orbital order for convenience. The 3 planets that have attracted the most interest for habitability are 1e, 1f, and 1g. These 3 orbit in or near the habitable zone of the star, where temperatures could, in principle, allow liquid water to exist on their surfaces. Let us be careful here, as we have been throughout. Being in the habitable zone does not guarantee liquid water. It does not guarantee an atmosphere. It does not guarantee habitability. It is a starting point. But it is a starting point that places 1e, 1f, and 1g on the short list of the most interesting planets we know of. All 3 are similar in size to Earth. 1e is just a little less massive, 1f is very close to Earth's mass, and 1g is a bit larger. They are rocky worlds orbiting a star that is stable, if different from our own. They have been there for billions of years. The system is estimated to be around 7 or 8 billion years old, much older than our solar system. That is a long time for chemistry to do its work, a long time for life to possibly get started, if the conditions were right. One of the key questions about the TRAPPIST-1 planets is whether they have atmospheres at all. This is not a given. Red dwarf stars like TRAPPIST-1 have a reputation for being temperamental, especially in their youth. They can produce powerful flares and bursts of radiation that might strip away the atmosphere of a closely orbiting planet. All 7 of the TRAPPIST-1 planets orbit very close to their star, well within the range where this kind of atmospheric erosion is a concern. It is possible that some or all of them are bare rocks, their atmospheres long since scoured away by stellar activity. Or it is possible that they have retained thick atmospheres, or that volcanic activity has replenished them over time. We simply do not know yet. And finding out is one of the main tasks that the James Webb Space Telescope has been assigned. Webb has been observing the TRAPPIST-1 system. The observations are difficult because the star is small and the planets are small, and the signals are faint. But the early results have begun to trickle in. As of now, the data suggests that the innermost planets, 1b and 1c, do not have thick, puffy atmospheres. That is not a surprise. They are the closest to the star, the most exposed to its radiation. The results for the planets in the habitable zone are still pending, or still being analyzed. No clear biosignatures have been confirmed anywhere in the system. The work is ongoing, and it will take years, probably many years, to build up a complete picture of what these 7 worlds are actually like. But the TRAPPIST-1 system, even without confirmed atmospheres or biosignatures, serves an important purpose. It is a concrete example. When we talk about exoplanets in the abstract, the numbers can become overwhelming. Thousands of planets, billions of stars. It is hard to hold any of it in the mind. But TRAPPIST-1 is specific. It has a name you can remember. It has 7 planets, and you can count them on one hand with fingers left over. It is close enough that you can imagine it as a real place, a physical location in the galaxy, with coordinates and dimensions and a faint reddish star at its center. It gives the search a kind of anchor, a place to return to when the abstractions get too large. And the system is not alone. There are other nearby stars with interesting planets. The star Proxima Centauri, which is the very closest star to our Sun, at just over 4 light-years away, has at least one planet in its habitable zone, called Proxima Centauri b. It is a red dwarf too, with all the same questions about flares and atmospheres. The star LHS 1140, about 49 light-years away, has a rocky planet in its habitable zone that is a prime target for atmospheric study. The star K218, about 124 light-years away, has a planet that is larger than Earth but smaller than Neptune, and Webb has already detected hints of water vapor and other molecules in its atmosphere. The list of interesting nearby systems is growing, and TRAPPIST-1 is just one entry on that list, a particularly rich and well-studied entry, but not the only one. It is easy when talking about these systems to slip into the language of hope, to imagine the surfaces of these planets, to picture oceans and continents and maybe even something stirring in the water. But the real state of our knowledge is much more modest. We know the sizes and masses of the TRAPPIST-1 planets. We know their orbits. We have some early data on the atmospheres of the inner 2, and that data suggests bare rock rather than thick gas envelopes. For the habitable zone planets, we are still waiting. We do not know if they have atmospheres. We do not know if they have water. We do not know if they have anything that could be called life. They are planets of possibility, not planets of certainty. And yet, the possibility itself is worth something. A few decades ago, we did not know if there were any planets around other stars at all. Now we know of thousands. A few decades ago, we could not have imagined a system like TRAPPIST-1, 7 Earth-sized worlds packed into an orbit smaller than Mercury's. Now it is a catalogued, named, and actively studied place. The pace of progress, measured over a human lifetime, has been remarkable. But that progress has not yet reached the point of answering the big question. It has only brought us to the threshold of being able to ask it properly. The TRAPPIST-1 planets will be studied for decades. Each new observation will add a piece to the puzzle. If the habitable zone planets turn out to have atmospheres, the next step will be to look for water vapor, for carbon dioxide, for the chemical signs of geological activity. If those are found, the next step will be to look for the harder-to-detect gases, the oxygen, the methane, the things that might point toward biology. Each step requires better instruments, more telescope time, more patience. The final answer, if it ever comes, may come from a telescope that has not been built yet, using techniques that have not been invented yet, by people who are not born yet. The search stretches across generations, and TRAPPIST-1 is one of the places where that generational baton is being passed. So as you lie here in the dark, you can, if you like, picture the TRAPPIST-1 system in your mind. Picture the small, cool star, glowing red and steady. Picture the 7 planets, arrayed around it like the notes of a scale. The inner ones too hot, baked by the star's radiation. The outer one too cold, drifting near the edge of the system's gravitational grip. And in the middle, the 3 that sit in the region where temperatures could be, in theory, just right. They are rocky. They are old. They may have atmospheres, or they may not. They may have oceans, or they may not. They may be dead, or they may be alive. Right now, as you breathe in and out, photons from the TRAPPIST-1 star are arriving at the James Webb Space Telescope, carrying whatever faint chemical signatures those planets possess. The data is being recorded, the analysis is underway, and we do not know yet what the answer will be. We only know that the question is being asked, carefully and patiently, of one specific star system, 40 light-years from the room where you are resting. That is a quiet thing to know. It is enough, for now, to let the mind wander there, to that distant red sun and its 7 worlds, and then to let the mind come back, softly, to the dark and the quiet, and the slow rhythm of your own breath. It is enough, for now, to let the mind wander there, to that distant red sun and its 7 worlds, and then to let the mind come back, softly, to the dark and the quiet and the slow rhythm of your own breath. Up until this point, we have been talking about looking at Mars through the eyes of rovers, looking at the icy moons through the instruments of passing spacecraft, looking at distant exoplanets by watching their stars dim and reading the faint fingerprints in their light. All of these methods are forms of searching with our eyes, broadly speaking, gathering light across the electromagnetic spectrum and analyzing it for signs of chemistry, of water, of conditions that might support life. But there is another approach, a different sense we can use. We can listen. The search for intelligent life beyond Earth, the kind of life that might build things, send signals, or otherwise make its presence known across interstellar distances, has its own history, its own methods, and its own long, patient silence. This branch of the search is often called SETI, which stands for the Search for Extraterrestrial Intelligence. It is not about finding microbes in Martian rocks or biosignatures in exoplanet atmospheres. It is about finding evidence of technology, of minds, of someone else out there who is trying, intentionally or not, to be heard. The logic behind SETI is straightforward. If there is another civilization somewhere in the galaxy, and if it has reached a level of technological development comparable to or beyond our own, it might produce signals that we could detect. These signals could be intentional, a beacon, a message, a deliberate attempt to say, "We are here." Or they could be unintentional, the leakage of radio communications, the hum of industrial activity, the kinds of signals that our own civilization has been spilling into space for over a century. Either way, the idea is to tune in, to scan the sky with sensitive radio receivers, and to look for patterns that cannot be explained by natural sources. Why radio? Because radio waves travel well through interstellar space. They are not easily absorbed by dust and gas. They can cross vast distances without losing too much of their structure, and they can be generated with relatively modest amounts of energy, at least compared to other kinds of signals. A civilization with technology like ours could, in principle, send a detectable radio signal across thousands of light years if it chose to do so. And we, with our radio telescopes, could, in principle, hear it. The SETI approach has been pursued in a serious, scientific way since the 1960s. The astronomer Frank Drake conducted one of the first modern SETI experiments in 1960, using a radio telescope in West Virginia to listen to two nearby stars. He called the project Ozma, after a character from the Oz books. He heard nothing unusual. The stars were quiet. But the idea took hold, and in the decades since, SETI has grown into a sustained, if modestly funded, scientific effort. The SETI Institute, based in California, has been at the center of much of this work. Researchers there use large radio telescopes to scan the sky, often targeting specific stars that are thought to have planets. They use sophisticated computer algorithms to sift through the noise, looking for narrow-band signals that are concentrated at a specific frequency, the kind that nature rarely produces, but that a transmitter easily could. Natural radio sources, like stars and galaxies and clouds of gas, tend to produce broadband signals. Their energy is spread out across many frequencies, like the static hiss between stations on an old radio. A narrowband signal, by contrast, is like a single clear note, a tone at one precise frequency. When radio astronomers find a narrowband signal coming from a point in the sky, it gets their attention. Most of the time, these signals turn out to be human-made interference, a satellite passing overhead, a cell phone tower, a piece of equipment that is not properly shielded. The work of SETI is largely the work of filtering out this terrestrial noise, of distinguishing the local from the cosmic. It is painstaking, methodical work, and it mostly returns negative results. But every so often, a signal comes through that is not immediately identifiable. And then, for a little while, the attention sharpens. The most famous such signal is the one known as the WOW signal. On August 15, 1977, a volunteer astronomer named Jerry Eman was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope had been scanning the sky as part of a SETI survey. On the printout, Eman noticed a sequence of numbers and letters that indicated a very strong, narrow-band signal at the frequency of 1,420 MHz, a frequency that, interestingly, is near the emission line of neutral hydrogen, the most abundant element in the universe. It is a frequency that some scientists had suggested would be a natural hailing channel for any civilization trying to get noticed. The signal lasted for the full 72 seconds that the telescope's beam was pointed at that patch of sky. Its intensity rose and fell in a pattern consistent with a fixed source moving through the beam, and then it was gone. Eman circled the sequence on the printout and wrote, "WOW," in the margin. That is the signal's entire name. The WOW signal has never been detected again. Telescopes have returned to that patch of sky many times, scanning the same frequencies, looking for a repeat. Nothing. No pattern, no repetition, no follow-up. Without a repeating signal, it is impossible to study it further, to determine its origin, or to rule out the possibility that it was some form of terrestrial interference or a glitch in the equipment. Most scientists who have looked at the evidence believe that the WOW signal was probably not a message from aliens, but it has never been definitively explained either. It sits in the history of SETI as a tantalizing anomaly, a maybe that could not be turned into a yes or a no. It is a reminder of how difficult this search is, and how easily a single piece of data can remain ambiguous forever. While we have been listening, we have also, on a few occasions, sent messages of our own. The most famous of these is the Arecibo message of 1974. The Arecibo Observatory in Puerto Rico had just been upgraded with a powerful new transmitter, and the team there decided to mark the occasion by sending a brief, symbolic radio message toward a globular star cluster called M13, about 25,000 light-years away. The message was encoded as a series of binary digits, ones and zeros, that, when arranged in a grid, formed a simple picture. The picture included representations of the numbers 1 through 10, the atomic numbers of key elements, a schematic of a DNA molecule, a stick figure of a human being, and a diagram of the solar system. It was not a serious attempt to communicate with aliens. It was more of a demonstration, a proof of concept, a way of saying that we, as a species, could, if we wanted to, send a message to the stars. The Arecibo message will take about 25,000 years to reach its target. By the time it arrives, the star cluster will have moved, and the message will miss its intended recipients. It is, in a sense, a message in a bottle thrown into an ocean we cannot cross. But it represents something important. It represents the other side of the listening coin, the desire not just to hear, but to be heard. The search for intelligent life is, at its core, a search for connection. It is the hope that somewhere out there, someone else is also listening, also wondering, also looking up at their own night sky and asking the same question. But we must be plain about the results. Despite decades of listening, despite the thousands of hours of telescope time, despite the ever-improving sensitivity of the receivers, no confirmed signal from another civilization has ever been found. The sky, as far as SETI can tell, is quiet. Not silent, there is plenty of natural radio noise, the hum of the galaxy, the crackle of pulsars, the faint whisper of the cosmic microwave background. But in terms of artificial signals, narrow-band transmissions, the deliberate or accidental broadcasts of another intelligent species, we have heard nothing. Zero confirmed detections. This is a fact worth sitting with. It is not a failure. It is a data point. The search is still young, and the volume of space we have actually searched is, in galactic terms, minuscule. But the null result is, for now, the result we have. There are many reasons why this might be the case. We will explore some of them more fully in the next section, when we sit with the quiet of the sky and the questions it raises. For now, it is enough to note that the silence is not a verdict. It is an observation. The galaxy could be teeming with life that does not use radio. It could be teeming with civilizations that use radio but do not broadcast in our direction. It could be that we have been listening for a cosmic eye blink, and that a sustained search over thousands or millions of years would eventually pick something up. Or it could be that we are, in fact, the only ones here. All of these possibilities remain open. The search continues. What makes the listening approach distinct from the looking approach is that it targets a different kind of life. The search for biosignatures in exoplanet atmospheres is a search for any life, even the simplest. A single-celled organism, a mat of algae, a microbe in a subsurface ocean. These could, in theory, leave chemical traces that we could detect from afar. But they would never build a radio transmitter. They would never send a message. The search for intelligent life assumes something more. That evolution, somewhere, has produced not just life, but minds, and that those minds have produced technology, and that those technologies are generating signals we can detect. Each of these steps is a filter. Life may be common, but complex life may be rare. Complex life may be common, but intelligence may be rare. Intelligence may be common, but technology may be rare. And technology may be common, but the willingness or ability to broadcast across interstellar distances may be rare. Each filter reduces the number of civilizations we might expect to hear from. We do not know how fine these filters are. The silence of the sky is, in part, a measure of how many other minds are out there and how loudly they are speaking. But that is a question for the next section. For now, let us stay with the listening itself. Picture a radio telescope, a large dish aimed at the sky, slowly scanning across the field of stars. Picture the control room, where a researcher sits with a cup of coffee, watching the data stream in. Most of what they see is noise. Most of what they hear is static, but every so often something stands out, a spike, a tone, a pattern that does not fit, and for a moment there is a flutter of attention, a quickening of the pulse. Then the signal is checked against known sources of interference. It is traced, analyzed, compared, and almost always it turns out to be us. a satellite, a radar, a phone, a piece of our own civilization's electromagnetic chatter bouncing back at us from the sky. The researcher notes it, logs it, and moves on. The quiet returns. The search continues. It is a strange and lovely thing, this listening. It requires a kind of patience that is hard to cultivate in a fast-paced world. It requires sitting with uncertainty, with the very real possibility that a lifetime of work will yield no positive result. And yet people do it. They do it because the question is worth asking, even if the answer is a long time coming, even if the answer never comes at all. There is something deeply human about cupping a hand to your ear and leaning into the dark, hoping to catch a whisper. The SETI researchers are doing, with vast and sensitive instruments, what our ancestors did when they sat around fires and listened to the sounds of the night, wondering what else was out there and whether anything was wondering back. So as you drift deeper into rest, you might imagine yourself as part of that listening, not with your ears, not actively straining to hear, but just by being here, by being part of a species that has learned to listen to the stars. The radio waves are passing through this room right now, the faint hum of the galaxy, the whisper of the cosmic background, and somewhere, perhaps, threaded into that noise, a signal we have not yet learned to recognize. Or perhaps not. Perhaps the quiet is complete. Either way, the listening is a gentle thing. It does not demand an answer. It only requires that we keep the channel open, keep the instruments running, and keep our minds receptive to whatever may come, or not come, out of the dark. Either way, the listening is a gentle thing. It does not demand an answer. It only requires that we keep the channel open, keep the instruments running, and keep our minds receptive to whatever may come, or not come, out of the dark. And that brings us to a question that has been sitting quietly in the background of this entire journey. It is a question that arises naturally from everything we have talked about so far, from the billions of stars, the thousands of planets, the ancient history of our own wet and living world, the decades of listening, and the silence that has greeted us. If the galaxy is so vast, and if it has been around for so long, and if the ingredients for life seem to be widespread, then why has no evidence of other civilizations been found? Where is everybody? That question, put in those simple words, is known as the Fermi Paradox. It is named after the physicist Enrico Fermi, who, during a casual lunch conversation with colleagues in 1950, is said to have asked something along those lines. The story goes that the group was discussing the likelihood of intelligent life in the galaxy, and Fermi, after a pause, looked up and asked, "But where is everybody?" He was not the first person to wonder about this. The paradox had been articulated in various forms before, but his name became attached to it, and the question has resonated ever since. The Fermi paradox is not a scientific theory. It is not a proven fact. It is a puzzle, a tension between two ideas that both seem plausible, but that point in opposite directions. On one hand, we have the scale of the universe. There are, in our galaxy alone, something like 200 billion stars. Many of those stars have planets. Many of those planets are rocky and orbit in habitable zones. The galaxy is about 13 billion years old. Our own planet formed about 4.5 billion years ago, and life appeared on it not long after the surface cooled and water could pool. That suggests that the origin of life, at least on Earth, was not an impossibly slow process. It happened as soon as the conditions allowed. If our experience is typical, then life should be common, and if life is common, then given the immense age of the galaxy, some of that life should have had plenty of time to evolve intelligence, develop technology, and spread out across the stars. A civilization that arose even a few million years before ours, a tiny fraction of the galaxy's age, could have colonized vast portions of the galaxy by now, using technology we can already imagine. So where are they? Why do we not see any evidence of them? On the other hand, we have the evidence, or rather the lack of it. We have looked, we have listened, We have scanned the skies with telescopes sensitive enough to detect a cell phone signal from another star system. We have searched for signs of large-scale engineering projects, Dyson spheres, for instance, which are hypothetical structures built by a civilization to capture the energy of its star. We have found nothing, no confirmed signal, no unmistakable artifact, no visitor at our door. The sky, as far as our instruments can tell, is empty of intelligent company. The silence is not absolute. There are plenty of natural phenomena making noise, but there is no whisper of another mind. This is the paradox. The expectation and the observation do not match. Something is wrong with one of our assumptions, or with several of them, or perhaps we have not been looking long enough or in the right way. The Fermi Paradox does not give us an answer. It gives us a framework for thinking about the question. And over the years, scientists and philosophers have proposed many possible resolutions. One of the most straightforward resolutions is that life itself is rare. We know that the basic chemical building blocks of life are common in the universe. Organic molecules have been found in interstellar clouds, in comets, in meteorites. But knowing how to go from a soup of organic molecules to a self-replicating system, a cell, a metabolic cycle, something that can evolve, remains one of the great unsolved problems in science. We do not know how it happened on Earth. We have not been able to recreate it in a laboratory from scratch. It may be that the origin of life is an extraordinarily unlikely event, one that requires a very specific set of conditions that happen to have occurred here and perhaps nowhere else, or almost nowhere else. If that is the case, then the galaxy could be full of habitable planets that are completely sterile, and the silence would make perfect sense. A related possibility is that life is common, but complex life, multicellular organisms, with specialized tissues and organs, is rare. Life on Earth remained single-celled for the vast majority of its history. The first microbes appeared perhaps 3.5 to 3.8 billion years ago. The first multicellular organisms of any complexity did not appear until about 600 million years ago. That is a gap of roughly 3 billion years, during which life was abundant but simple. It may be that the transition from simple to complex is a very difficult hurdle, one that requires a rare combination of environmental stability, genetic innovation, and sheer luck. If that is the case, then the galaxy might be full of microbes but empty of plants, animals, and minds. Then there is the possibility that intelligence and technology are the rare steps. Even if complex life evolves, it does not automatically lead to intelligence of the kind that builds radio telescopes and spaceships. The dinosaurs were complex and successful, and they dominated the Earth for over 100 million years, but they never built a radio transmitter. Intelligence like ours, the kind that invents calculus and builds machines and wonders about the stars, may be the result of a very specific and unlikely set of evolutionary pressures. And even if intelligence does arise, it may not lead to technology. There could be intelligent beings living in oceans, with no access to fire or metallurgy, who spend their lives thinking deep thoughts but never send a signal into space. Or there could be intelligent beings who simply have no interest in communicating with the stars, who find their fulfillment in art or contemplation or social life, and who never build the tools we are listening for. Another class of resolutions involves time. The galaxy is old, but civilizations may be short-lived. Our own technological civilization, the one that can send and receive radio signals, has existed for barely a century. That is a tiny sliver of geological time. If civilizations tend to destroy themselves through war or environmental collapse or some other self-inflicted catastrophe, then they may appear and disappear so quickly that they never overlap in time. The galaxy could be full of civilizations that have risen and fallen, one after another, like sparks flying up from a fire, each one burning brightly for a moment and then going dark. We could be listening at a time when no one else happens to be broadcasting. The silence would not mean we are alone. It would mean we are out of sync. There is also the possibility that advanced civilizations are out there, but are deliberately quiet. They might be hiding, observing from a distance, adhering to some principle of non-interference. Or they might be communicating in ways that we cannot detect, using technologies that we have not yet invented, on frequencies we have not thought to scan, with signals that look to us like noise or like nothing at all. Our own radio leakage is becoming less detectable as we move toward more efficient, lower-power communication methods like fiber optics and tight beam transmissions. A truly advanced civilization might have no detectable electromagnetic signature at all, its communications compressed and directed in ways that leave no stray signal for us to overhear. And then there is the possibility that we are simply wrong about the ease of interstellar travel. Even if a civilization were long-lived and expansion-minded, the distances between stars are enormous. The energy requirements for crossing them, even at a significant fraction of the speed of light, are staggering. It may be that interstellar colonization is simply not practical, or not worth the cost, or that it proceeds so slowly that the galaxy has not yet been filled. A civilization might spread in slow waves, taking millions of years to cross a single spiral arm, and we might just happen to live in a region that has not yet been reached. These are some of the proposed resolutions to the Fermi Paradox, and they are not mutually exclusive. The real answer could be a combination of several of them. Life might be somewhat rare, intelligence rarer still, and the window for detecting signals might be narrow. Put them all together, and the silence becomes less of a paradox and more of a statistical inevitability. Or life might be common, intelligence common, and the galaxy might be buzzing with signals that we simply do not yet have the right tools to hear. The important thing to understand, and to sit with, is that the Fermi Paradox is genuinely unresolved. Physicists and astronomers and biologists and philosophers argue about it, and no single explanation has convinced everyone. Some scientists think the silence is deeply meaningful, a sign that we are probably alone, or nearly alone, in the galaxy. Others think the silence is an artifact of our limited search, and that we have barely scratched the surface of what there is to find. The debate is active, and it is unlikely to be settled without actual evidence, the very evidence we have not yet found. There is a way of framing the Fermi Paradox that can feel unsettling, as if the silence is a kind of cosmic loneliness, a void where we hope to find company. But there is another way to hold it, a quieter and more restful way. The silence is not a verdict, it is a space. It is an open question large enough to hold all of our wondering without crowding it. The fact that we do not know why the sky is quiet means that many possibilities are still in play. The galaxy could be empty, or it could be full. We do not know. And not knowing is not the same as being lost. It is the same as being at the beginning of a search that has barely gotten underway. Think of it this way. Imagine you are standing on a beach at night, looking out at a dark ocean. You cannot see the far shore. You cannot see any ships. The only sound is the wash of the waves. Does that mean the ocean is empty? Or does it mean that the ocean is vast and your vision is limited, and the ships, if they are out there, are far beyond the reach of your sight? The Fermi Paradox is the acknowledgement that we are standing on that beach, and that the ocean is very large, and that we have only just begun to look. The silence is not a failure. It is the starting condition of the search. It is what makes the search meaningful. So as you rest, let the silence be spacious rather than troubling. Let it be a quiet room, not an empty one. The Fermi Paradox is not a problem to solve tonight. It is a question to drift inside, a puzzle that has no deadline and no required answer. The stars are out there, and they are quiet, and that quiet has many possible explanations. Some of those explanations are mundane, some are profound, none of them are confirmed. And so the question stays open, and the search continues, and the night remains what it has always been, a vast, dark canvas for our wondering. And so the question stays open, and the search continues, and the night remains what it has always been, a vast, dark canvas for our wondering. Now, as we begin to draw this long, slow journey toward its close, it is worth turning our attention to the near future, not the distant future of interstellar travel or contact with alien civilizations, but the next years, the next decade or two. The quiet, ongoing work that is already planned, already funded, already underway. The missions that are currently in space, cruising toward their destinations, or being assembled in clean rooms, or being designed on drawing boards. These are not science fiction. These are real efforts with real teams, real budgets, and real timelines, and they represent the next chapter in the search we have been tracing through the dark. The James Webb Space Telescope, which we have mentioned several times already, is at the forefront of this work. Webb is not a one-mission instrument. It is designed to operate for many years, perhaps 10 or more, depending on how its fuel and its instruments hold up. Over those years, it will continue to observe exoplanet atmospheres, refining the data we have on the TRAPPIST-1 planets, on Proxima Centauri b, on LHS 1140b, on K218b, and on many others that are yet to be fully studied. Each new observation adds a piece to the puzzle. Each spectrum of a planet's atmosphere is a small step toward understanding what kinds of atmospheres exist, how they form, and whether any of them show the chemical fingerprints that we associate with life. Webb will not answer the big question by itself. No single telescope will. But Webb is building the foundation. It is creating the catalog of atmospheric data that future telescopes will build upon. It is, in a very real sense, writing the first draft of the Encyclopedia of Exoplanet Atmospheres. At the same time, the search within our own solar system is entering a new phase. 2 major missions are currently on their way to the Jupiter system, both aimed at studying the icy moons we talked about earlier, the moons with the hidden oceans. These missions are not small, quick flybys. They are large, complex, multi-year efforts, each designed to spend years in the Jupiter system, making repeated close passes of the moons and gathering data of unprecedented detail. The first of these is the European Space Agency's JUICE mission. JUICE stands for Jupiter Icy Moons Explorer. It launched in April of 2023, and it will take about 8 years to reach Jupiter, arriving in the early 2030s. Once there, it will spend several years studying the Jovian system, with a particular focus on 3 moons, Ganymede, Callisto, and Europa. All 3 are thought to have subsurface oceans. Ganymede, the largest moon in the solar system, is actually larger than the planet Mercury, and it is the only moon known to have its own intrinsic magnetic field, a sign that it has a liquid, conducting interior. JUICE will eventually enter orbit around Ganymede, the first time a spacecraft has ever orbited a moon other than our own. It will map the surface, study the ice shell, and probe the moon's magnetic and gravitational fields to learn more about the ocean that is thought to lie beneath. It will also make multiple flybys of Europa and Callisto, gathering data that will complement the other mission heading to Jupiter. That other mission is NASA's Europa Clipper. Europa Clipper launched in October of 2024, and it is taking a faster route to Jupiter, arriving around 2030. Unlike JUICE, Clipper is focused almost entirely on Europa. It will not orbit Europa directly. The radiation environment around Jupiter is too intense for that, but it will make dozens of close flybys, swooping in low over the moon's surface and then pulling back out to safer distances. Each flyby will bring it within tens of kilometers of the surface, allowing its instruments to map the ice shell in detail, to measure its thickness and its structure, to search for pockets of liquid water within the shell itself, and to analyze the composition of the surface. One of the key goals is to understand whether Europa's ocean has the chemical ingredients that life would need, and whether there are pathways for those ingredients to mix between the ocean, the ice, and the surface. The plumes of water vapor that have been tentatively detected from Europa are also a target. If Clipper can fly through a plume, it could sample the ocean directly, much as Cassini sampled the plumes of Enceladus. That would be a major advance, a taste of an alien ocean, analyzed by instruments built for exactly that purpose. These missions are not designed to detect life directly. They do not carry microscopes that could identify a microbe. They are designed to study habitability, to understand whether Europa and Ganymede have the conditions that life needs, and to lay the groundwork for a future mission that might one day land on the surface and drill through the ice. That future mission is still a long way off, probably decades, and it will be enormously difficult and expensive. But JUICE and CLIPPER are the necessary first steps. They are the scouts, the advance teams, the ones that will map the terrain so that the next generation can know where to look. Beyond Jupiter, there is also quiet interest in returning to Saturn's moons, particularly Enceladus. No mission is currently approved and funded for that, but the concept studies are underway. The discoveries Cassini made at Enceladus were so striking that there is a strong scientific case for going back with a dedicated mission. Perhaps an orbiter that could spend years studying the plumes, or even a lander that could touch down near the South Pole and collect fresh material from the vents. That mission, if it ever flies, is still in the future. It is a possibility, not a plan, but it is the kind of possibility that keeps the search moving forward, one step at a time. And then there is Mars. The Perseverance rover is still working, still collecting samples in Jezero crater. Those samples, sealed in metal tubes, are meant to be retrieved by a future mission and brought back to Earth. The Mars Sample Return Campaign is one of the most ambitious things ever attempted in planetary science. It involves landing a fetch rover, loading the samples into a small rocket, launching that rocket from the surface of Mars, and capturing the sample container in orbit for the return trip to Earth. The technical challenges are enormous, and the timeline keeps slipping. It may not happen until the 2030s or even later, but the samples are there, waiting on the surface, a cache of rocks that could contain the first definitive evidence of past life on another world. Or they could contain nothing but interesting geology. Either way, they represent the next major step in the exploration of Mars. Closer to home, ground-based telescopes are getting bigger and more capable. The European Southern Observatory is building the extremely large telescope in Chile, with a mirror nearly 40 meters across. When it comes online later this decade, it will have the resolving power to directly image some of the nearest exoplanets, to separate their faint light from the glare of their stars, and to take spectra of their atmospheres in ways that complement Webb's observations. Other giant telescopes are planned, each one pushing the boundary of what we can see and measure from the surface of our own planet. The search is not limited to space. It is happening on mountaintops in the Atacama Desert, on the summit of Mauna Kea in Hawaii, in control rooms and data centers and university offices around the world. All of this work, the telescopes, the spacecraft, the missions to the outer planets, shares a common pace. It is slow, it is deliberate, it is measured in years and decades, not days and weeks. The people who work on these missions often spend their entire careers on a single project. They know that the big answers, if they ever come, will probably come after they have retired or after they have died. And yet they do the work anyway. They do it because it is worth doing. They do it because the question, are we alone? Is there life out there? What else moves in the dark? Is one of the most profound questions a person can ask. And every small piece of data, every new spectrum, every close flyby of an icy moon is a step toward an answer. This is not a search that will end with a dramatic announcement on the evening news. It is far more likely, if the answer turns out to be positive, that it will arrive slowly, over years, as evidence accumulates and the scientific consensus gradually shifts. First, we might find an atmosphere on a rocky exoplanet. Then we might find water vapor in that atmosphere. Then we might find a combination of gases that is hard to explain without biology. Then the debate will begin. Is it really life, or is there some non-biological process we have not thought of? The debate will go on for years, perhaps decades. New instruments will be built to settle it. Observations will be made, papers will be published, arguments will be had, and slowly, carefully, the picture will come into focus. That is how real discovery works. It is not a lightning bolt. It is a sunrise, gradual, incremental, and visible only to those who are patient enough to watch the whole sky brighten. So as you can rest in the knowledge that the search is in good hands. The missions are flying, the telescopes are observing, the The data is accumulating. The next years will bring new results, new questions, new refinements of what we know and what we do not know. Some of those results will make headlines. Most will not. Most will be published in journals that only specialists read, and they will add one more data point to a picture that is still far from complete. But each data point matters. Each one is a small thread in the larger tapestry. And the tapestry is being woven right now. At this very moment, the James Webb Space Telescope is pointing at some distant star, measuring the dip in its light as a planet crosses its face. The Europa Clipper is coasting through interplanetary space, carrying its instruments toward a rendezvous with an ocean world. The Perseverance rover is sitting in Jezero crater, its sample tubes filled with rocks that may one day be brought to Earth. The radio dishes of the SETI search are scanning the sky, sifting through the static for a signal that does not fit. All of this is happening, quietly, persistently, while you lie here in the dark. The search does not sleep, it does not pause. It just keeps going, night after night, year after year, generation after generation. And that is a comforting thought, in its own way. The question is being held for us. We do not have to solve it ourselves. We do not have to stay awake worrying about it. We can let go, let our eyes close, and trust that the work is being done. The answer, if it comes, will come in its own time. And if it does not come, if the silence remains unbroken, if the spectra show nothing but rock and gas and ice, then that too is an answer of a kind. It tells us something about our place in the universe. It tells us that we may be rarer than we thought, or that the universe is quieter than we hoped, or that the conditions for life are more finely tuned than we imagined. And that knowledge, too, is worth having. The search is not only about finding company, it is about understanding the nature of the cosmos and our place within it. Every outcome teaches us something. Every outcome is worth the effort. Every outcome teaches us something. Every outcome is worth the effort. And so we arrive at the end of this long, slow walk, not at a conclusion, not at a final answer, but at the quiet edge of the question itself. The question that has been with us since the beginning, since the ancient philosophers looked up at the dark Mediterranean sky, since Schiaparelli drew his channels on Mars, since Lowell imagined a dying civilization building canals, since the first radio telescopes turned their dishes toward the stars and listened. Are we alone? Is there life somewhere out there, beyond this planet, beyond this solar system, beyond the familiar stars we can see with our own eyes? The search has been going on for a very long time, in one form or another, and it has not yet found a confirmed answer. That is the plain fact. Humanity has looked and listened and wondered and sent machines to other worlds and built telescopes of extraordinary power and sifted through mountains of data, and what we have found, so far, is a universe rich with possibility. We have found ancient riverbeds on Mars and organic molecules in its rocks. We have found hidden oceans on moons of Jupiter and Saturn, kept liquid by the warmth of tidal heating, venting water vapor and hydrogen and organic compounds into space. We have found thousands of planets around other stars, many of them rocky, many of them in the habitable zones where liquid water could, in theory, pool on their surfaces. We have begun to read the atmospheres of some of those planets, looking for the chemical fingerprints that might point toward biology. We have scanned the radio spectrum for signals from intelligent civilizations, and we have heard nothing that could be confirmed as artificial. The search has been broad and deep, and remarkably successful in mapping the landscape of possibility, but it has not yet found life. This is not a failure. It is not a disappointment in any urgent sense. It is simply the state of the search as it stands tonight, in the early decades of the 21st century, after a few generations of serious scientific effort. We are at the beginning of this, not the end. The tools we have now are vastly better than the tools we had 50 years ago. The tools we will have 50 years from now will be vastly better still. The search is accelerating, not winding down, but it is also, by its nature, slow. It requires patience. It requires the willingness to sit with an open question for longer than a single human lifetime. And the open question, the not knowing, is not a source of anxiety. It is a kind of spaciousness. It is room to breathe. It is the recognition that the universe is larger and stranger and more full of possibility than our current understanding can capture. If we already knew the answer, if we had already found life, or already proven we were alone, the question would be closed. The wondering would be over. There is a certain loss in that, a closing of a door. Right now, the door is still open. The possibility is still alive. The search is still underway. And that open door is a gentle thing to rest beside. Earth, so far as we know, is the only confirmed home of life in the universe. That is a quiet fact, a sober fact, but not a lonely one. Look at what Earth has produced. Look at the richness and variety of life on this planet alone. The forests, the oceans, the grasslands, the coral reefs, the microbes living in boiling springs and frozen ice, and deep, dark rock miles beneath the surface. Look at the complexity of a single cell, the intricate dance of proteins and nucleic acids that keeps the whole system running. Look at the slow, patient work of evolution, crafting and recrafting over billions of years, producing creatures of astonishing beauty and strangeness and adaptability. If Earth is the only place where all of this has happened, then Earth is, by any measure, extraordinary. It is precious, it is worth protecting and understanding and marveling at. The possibility that we might be alone does not diminish the value of what we have here. If anything, it heightens it. And yet, the possibility that we are not alone is still very much alive. Every new discovery in the search for exoplanets has reinforced the idea that planets are common. Every new study of extremophiles has reinforced the idea that life can thrive in conditions we once thought impossible. Every new analysis of the chemistry of interstellar space has reinforced the idea that the building blocks of life are everywhere. The ingredients are there. The environments are there. The time has been more than sufficient. The only thing missing is the evidence that the spark has actually caught somewhere else. And that evidence may come tomorrow, or in 10 years, or in 100 years, or never. We do not know. The not knowing is part of the search. It is what makes the search honest. There is a particular image that is worth holding in your mind as you drift toward sleep. It is the image of yourself, lying here in the dark, resting under the same sky that so many people, for so long, have looked up into with the same question. The sky that the ancient Greek philosophers saw, the sky that Schiaparelli and Lowell squinted into through their brass telescopes. The sky that Frank Drake aimed his radio dish toward in 1960, listening to 2 nearby stars and hearing only static. The sky that the Kepler Space Telescope stared at for years, measuring the tiny dips in starlight that revealed thousands of distant worlds. The sky that the James Webb Space Telescope is studying right now, pulling apart the light of alien suns into rainbows of chemical information. All of those people, all of those instruments, all of that effort, and the sky is still there, and the question is still open, and you are part of that lineage, simply by wondering. You do not need to be a scientist to be part of this. You do not need to understand the details of spectroscopy or the transit method or the chemistry of hydrothermal vents. You only need to be curious. You only need to be willing every now and then to look up and ask the old question, and to sit with the fact that the answer has not yet arrived. That willingness is, in itself, a kind of participation. It connects you to everyone else who has ever wondered. It connects you to everyone else who will wonder in the future. The search is not just a technical project. It is a human project, one of the most fundamental human projects there is. And it is carried forward not just by scientists and engineers, but by anyone who takes the time, on a quiet night, to think about the stars and what might be out there. So as you rest now, let the question be a soft presence, not a demanding one. You do not need to wrestle with it. You do not need to solve it. You do not need to stay awake turning it over and over. You can simply let it be there, in the background, like the faint hum of the universe itself. The search is in good hands. The telescopes are pointing. The spacecraft are flying. The data is being gathered. The analysis is underway. The answer, if it comes, will come in its own time, and it will come whether you are awake to hear it or not. You can let go. You can let your breathing slow. You can let your thoughts drift away from the specifics and into the general feeling of spaciousness, of openness, of a question that is large enough to hold a whole night's worth of wondering. Think of the Earth, turning slowly beneath you as you lie here. Think of the thin blue layer of its atmosphere, the only atmosphere we know of that is rich with oxygen, the only one we know of that carries the unmistakable chemical signature of a living world. Think of the oceans, warm and salt and full of motion, covering most of the planet's surface. Think of the ice caps, the deserts, the rainforests, the mountains, the plains. All of it, this whole intricate system, is the only confirmed home of life we have. It is enough. It is more than enough. And if it turns out to be the only one, then we are the luckiest creatures in the galaxy, whether we realize it or not, because we get to be the ones who live on the living world. We get to be the ones who look up at the dark sky and ask the question. We get to be the ones who wonder. And if it turns out that we are not alone, if somewhere on a planet orbiting a red dwarf 40 light-years away, or in the hidden ocean of an icy moon circling Jupiter, or in some place we have not even thought to look, there is something alive, then the wondering will take on a new dimension. It will become a conversation, a connection, a recognition across the vast distances of space and time. But even then, the wondering will not end. It will simply change shape. There will always be more to learn, more to understand, more to be curious about. The search is not a finite project with a finish line. It is an ongoing relationship with the unknown. And the unknown, as we have seen throughout this journey, is not something to fear. It is something to settle into, something to explore, something to let hold you gently as you drift off to sleep. So here we are, at the end of the walk, under the same sky we started under. The question is still open, the search is still patient, the night is still long, and you have nowhere else to be. You have done the wondering for tonight. You have walked through the history, the science, the possibilities, the mysteries. Now it is time to let it all go, to let the words fade into a soft murmur, to let your thoughts dissolve into the dark. The sky will still be there when you wake. The question will still be there. The search will still be underway. But for now, for this moment, you can rest. You can close your eyes and be part of the quiet, part of the stillness, part of the long, slow, patient wondering that connects every stargazer who has ever lived. Sleep well, under the same stars that have always held our questions, and that will hold them long after we are gone.